Yeah, let's do that.
You're not
Not yet.
Not yet.
Probably wrong.
Okay. Yeah.
Okay, good morning, everyone. So glad to have you back on the third day of the workshop. And today we have two sessions. The first in the morning is about biomass burning, which has attracted a lot of interest, especially if you can see the news, the wildfire in California, which is related to this. So we're going to have this in the morning, and in the afternoon, we are going to talk about the indoor air pollution. So let's welcome Professor Gaston and Wang for coordinating this morning session.
Great. Well, thank you everyone for joining us. So our first speaker is going to be Rebecca Sheasley from Baylor University. She's going to tell us about how aerosol composition and optical properties can tell us something about atmospheric aging. So that, give it to Professor Sheasley.
Yes, slides. Here. Perfect. Okay.
Hello, thanks for inviting me out here to Miami. This is a really fun experience to be able to come out here and talk to you guys and hear about the great work that you're doing on campus. I just wanted to acknowledge at the beginning here, a few of the people that have worked on this larger project. You'll probably recognize a couple of the names. Manisha Mehra and Sujan Shrestha have also been participating in this particular study over the long term. We also had collaborators at the University of Houston and collaborators at Aerodyne, one of the instruments that was mentioned yesterday in one of the short talks. We actually have here one of the TILDAS instruments. And then I want to acknowledge funding from TCEQ and the Texas Air Quality Research Program. So I just wanted to start out and say we're talking about biomass burning today. I'm going to sound really excited about it because I think it's really interesting. But obviously, when you look on the news, the news coming out of Los Angeles is super devastating. And those types of kind of local impacts and local exposure and impacts on people's homes and people's lives is kind of a different level of devastation. And you don't need an atmospheric chemist to come in and tell you that that's a bad thing, or come in and tell you that they've been exposed and there's lots of emissions that we have to worry about in those particular cases. So I just want to acknowledge that at the beginning, that I'm not going to sound as serious as that particular case may be. We're talking about more kind of on the scientific side, and also talking a little bit more on what happens when we have this transport of these huge plumes and transport of this pollution over long ranges. So we can think about kind of the initial state of that biomass burning plume and initial parameters that we might be interested in: chemical composition, the speciation of gas and particle phase emissions. We can think about the aerosol optical properties. If we're thinking about climate change, we might be interested in how much black carbon there is, how much brown carbon there is, what is the scattering, all of these different types of questions. So we have a lot of different parameters of interest that we can evaluate when we look at biomass burning plumes. We also, when we start thinking about the transport, we can think about how do these parameters change over time. A biomass burning plume is very dynamic, right? It's constantly changing. It's diluting. There's chemical reactions happening. There's partitioning happening between the gas phase and the particle phase. There are reactions happening in the gas phase and reactions happening in the particle phase. So there are a lot of different questions we may potentially ask, and there's a lot of changes happening if we do measurements at the plume at the initial combustion site versus 6 hours downwind, right? 12 hours downwind, 5 days, 10 days downwind. What types of changes would we expect to see in some of our parameters of interest? So we can have oxidation happening. And then if we think about the long-term impacts or the global impacts, we can think about changes in the associated radiative forcing over that time. So if we think about, if we're trying to say how much aerosol absorption is associated with that plume, we would want to know not only the black carbon composition and the black carbon concentration, we would also want to know about the brown carbon, right? So we can think about all of those things. And it's a lot to kind of hold in your head. I think of it as job security, right? There's an enormous number of questions that we can ask, and we're not close to having all the answers on that. And if you want to think a little bit about job security, I've technically been doing this since about 2000. So for 25 years, I've been working on this, and we still have a million questions. So there's a lot of job security associated with studying biomass burning. Once we think about the different questions that we would potentially have, because I'm an experimentalist, I think about what measurements would we like, right? So experimentalists will think of what measurements would we like. They'll also think of what instruments do I have access to? What do I have in my lab? Who can I get to show up where, to substantiate my measurements? So we can think about potentially detailed composition. If we have, a TOF AMS, if we have a PTRMS, we can think about the composition in the gas phase or the particle phase. We can think about particle size. We can think about optical properties. We can think about single particle. And then we can think about all the changes that are happening over time. If we then kind of go further on that and think about how would we do those measurements? What kind of experiment would we have? We can start thinking of things like campaigns versus long-term, right? So if you think about, I'm going to go out for a month and study biomass burning aerosols, you might think, I'm going to bring all of my most complex instrumentation. I'm going to have people sitting at that site and doing these measurements for a month. So I'll bring my high resolution TOF AMS. I will bring my SIMS. I will bring all of these different things. If you're thinking about a long-term measurement, you're thinking, oh, at this site over years and years and years, I want to know what the biomass burning impacts are. Not necessarily going to have the same suite of measurements, right? You're going to have a more refined list of instrumentation, more simple measurements that you could potentially have. So when we think of all of this, then we think of what measurement packages do we need to address these questions of aging? What kinds of information would we ideally like to have to answer some of these questions of aging, to answer them in detail and or to answer them over the long term? Before we get into that, let's talk a little bit about the aging of biomass. And I'm going to specifically focus more on brown carbon and the composition changes associated with that. So if we think about brown carbon in biomass burning plume, we can think about its initial generation. So it's from pyrolysis of lignin. So we can have these chromophores that are produced initially during combustion. And those are ones that then can be diluted and transported and reacted over time within that biomass burning plume. So recent work has indicated that we can also potentially have some of those initial oxidation steps can actually increase the absorption associated with brown carbon. So we can actually have more absorption associated with those brown carbon in the initial stages of oxidation in those biomass burning plumes. And then as we have additional oxidation steps, then we have some of that photo bleaching that you're familiar with. So you can have these kind of changes happening over time. It's not necessarily a linear change of just straight brown carbon to only scattering and no absorption. There are a lot of different things that affect that oxidation and affect those changes in the brown carbon. So you imagine a big biomass burning plume. It is not just a box, right? That's moving through time with exactly the same composition and the concentration within that box as it's moving through space and time. So you can imagine the edges of that plume are much more dilute might actually be oxidizing faster because they're more dilute. They have more access to sunlight. There may be more, they may look more aged at the edges of the plume than they do in the center of the plume. There have been studies that have seen that the center of a plume may not react very fast because it is so concentrated. The light isn't penetrating the way that it would on the edges. So we have all these different changes happening and have all these different processes that are impacted by the physical state of the plume as well. If we look at changes in specific chromophores, some of these nitrophenols, they can be produced by that lignin pyrolysis. They can be produced in the BB plume during, or biomass burning. I'm going to say BB probably a few times. They can be produced in the plume as they continue to react over time. You can see here, let's see, do I have a pointer? Yeah, I have a pointer. So you can see here, these are some of the kind of the end product oxidation products. So we go from having some brown carbon with initial oxidation steps actually kind of maintain that absorption, but that the later oxidation steps where you're breaking down those chromophores, you're losing some of that nitrogen, you're losing some of those heteroatoms, you actually start breaking down into these really common small organic acids. So if you're familiar with the studies by Kawamura that look over the Pacific Ocean, this is what you wind up with, right? You get to the end of the line with any type of carbonaceous plume, you wind up with a lot of these organic acids. And these can be marks of oxidative processing. They can also be like oxalic acid, a mark specifically of aqueous phase processing or cloud processing. So this means we have to start thinking about the physical parameters that biomass burning plume is encountering as it's being transported through space and time. Like we said, it's not just in a box with continuous conditions that whole time. So it can be moving through, it can be encountering clouds, it can be encountering changes in temperature and relative humidity. Those changes can then change the aerosol viscosity, which then changes some of these oxidation rates. So when we start thinking about the aging and the time of aging for some of these plumes, it's not always going to be exactly the same. The lifetime of some of these chromophores and the lifetime of some of this brown carbon is not always going to be consistent, and it is going to be affected by some of these. I just realized I'm going to interrupt myself. Where do I have an idea of my time so that I don't go over?
I'm gonna remind, so we start at 9:03.
Okay. Okay. Thank you. I just want, I'm being a professor and I'm kind of going off, and I just want to make sure that I'm connected to reality and I know what time I have. So if we think about this biomass burning plume being transported, there has been some work to estimate how the changes in altitude that it's being transported at, the changes in latitude, which would be associated with the changes in temperature and relative humidity that it's being impacted by, those can actually change the lifetime of some of that brown carbon. So if we start looking at areas where we might have shorter lifetimes of some of these brown carbon chromophores, we might think of low latitudes where the humidity is higher, the temperature is higher, lower latitudes and lower altitudes. If we have the biomass burning plume being lofted to high altitudes and being transported in a drier environment, we might have a longer lifetime associated with some of these, right? The temperature and the relative humidity is going to be lower. We're not going to have as much aqueous processing, we're not going to have as much cloud development. And so that we're going to see maybe longer lifetime of brown carbon at these higher altitudes than we would expect if the plume is being primarily transported close to the ground. So a lot of this, we can kind of try and keep this in our mind when we're thinking about some of our field campaigns. We're thinking about some of the monitoring data that we have access to. So we started in Texas and ran for 5 years, the BC2 Aerosol Optical Network. This is roughly based on the NFAN network that NOAA has in place. So we have the same aerosol optical measurements at these locations. There are similar instrumentation at the SGP site in Oklahoma, which is run by DOE. So you can see our timeline over here. We started in El Paso. We had sites for 3 years in Houston, and then also had sites for a year in Fort Worth. So I'm going to discuss a couple cases from this particular network. But the reason we put this network together was to have kind of longer term measurements and monitoring level measurements of aerosol optical properties that we could use to evaluate whether we were impacted by biomass burning plumes, and then in the end, whether we were impacted by dust plumes as well. And we're in these very different locations across Texas. So obviously the El Paso site had more local dust that we had to be concerned with. The Houston site and the Fort Worth site would have long-range transport of biomass burning, but also potentially long-range transport of dust. If we think about our approach and we think about the instrumentation that we had available, so the kind of backbone of our approach and the backbone of this site was aerosol absorption and scattering. And so we used a Brechtel tricolor absorption photometer and an Ecotech nephelometer. So the reason we used an Ecotech nephelometer, TSI does not make those anymore. And so we needed something that we could purchase quite a few of these nephelometers. So we used both of those. We used 2 absorption photometers at each site so that we would have a longer time frame between switching out filters. We had trace gas, CO, and ozone. And then for PM characterization, we would trigger filter sampling when we had a biomass burning event so that we could do additional speciation of that biomass burning plume. We were also co-located at TCEQ air monitoring sites, so we would often have NOx or weather data available as well. We also had a 2023 intensive campaign with Aerodyne where they brought a TILDAS that measured HCN. HCN is a gas phase tracer for biomass burning. So that was to kind of supplement the aerosol optical and also provide kind of additional very different types of information about the biomass burning plume that we couldn't necessarily see with the aerosol optical. So if we also think about that smoke and dust transport that we might be impacted, that might impact Texas, we can think of wildfires from the Western US, wildfires from Canada. We have different seasons of impacts in Texas. In the summer, we may have agricultural burning in the Southern US and Mississippi River Valley. In the winter and spring, we might be impacted by agricultural burning coming up from Mexico. In the late summer, or in this particular case, early summer, we might be impacted by wildfires from Canada. And as you all are very familiar with, we also have a lot of Saharan dust impacts. Routinely every summer, July and August, we'll see Saharan dust in Houston. And this network was very good about indicating to us exactly when that was happening. If we look at the data that comes out of that, this is kind of a depiction of 1 year's worth of data that we collected at one of our Houston sites, Aldine, which was the most urban of our sites. And what we see here, so if you're used to looking at aerosol optical data from a remote site, what you'll see, and this is the Kappa figure, you might see very distinct kind of source signatures. The biomass burning shows up really strongly as a high AAE, lots of brown carbon. The dust shows up really strongly in another corner with low SAE or high, lots of large particles, some absorption associated with minerals. So you may see kind of that really specific kind of source signatures popping out when you look at remote data sets. Looking at an urban signal is very different. So we have this kind of background black carbon, background fine aerosol. So we have that kind of stable composition that we're adding some of these transported sources to. So we're adding the biomass burning, we're adding the dust to the top of that. And it kind of pulls our urban signal in one direction or the other, but we don't typically see that super clean unless we're like heavily impacted by biomass burning. We don't necessarily see that super clean signal. So with that kind of background, I'm going to talk about two different case studies that we saw in 2023. And these are both cases where we weren't being impacted by local fires. We can have local fires in Texas. Recently, they haven't been quite as big. We did have a large Plains fire a couple years ago. But recently they haven't been quite as large as the Canadian wildfires or the wildfires that you would see on the West Coast. But these large wildfires can potentially impact Texas and can travel for long distances. If you're familiar at all with looking at satellite data, the visual data, you can actually see the smoke plumes coming from these large fires. So we want to ask questions about how do the atmospheric conditions during transport impact the composition and optical properties. Can these plumes be identified at these urban locations? So we have this urban background signal. Can we actually see this kind of dilute biomass burning plume impacting our urban sites? Can they be identified after the aging processes have happened? And when we start thinking about the potential conditions that they are encountering as they're being transported to Texas, they're going through different PBL regimes. There may be high boundary heights associated at lower latitudes. There may be changes in relative humidity that they're encountering. So we're trying to keep all of these kind of questions in mind as we start looking at our data. So I'm going to be a little bit confusing here. I'm going to talk about the June case study first and the May case study second. So we're not going chronologically. This was just a choice. So my initial event that I wanted to talk about was an event that we saw in June 2023 in the Houston area. So we have these 3 different sites that we have in Houston. Aldine is our urban site and Liberty is a rural site. But you can see this is the NOAA hazard mapping that shows the smoke plumes and also shows fires. So we can see that there's a lot of potentially like a small agricultural burning that's happening, prescribed fires at this point in time, but also this just massive kind of smoke column that we see over coming towards Aldine and Liberty. We can also see that at the same point in time, we have a lot of fires in Mexico. So our initial questions may be, if we're seeing kind of smoke impacts at Houston, where is that coming from? If we look at kind of the synoptic weather patterns, we can see that it's the smoke that's coming down from Canada that's actually impacting us. So do we see this in our measurements? If we look specifically at our AAE, which shows us when the AAE is higher, that's showing us that there's more brown carbon there. The absorption coefficient is the measurements that's most related to concentration. So when the absorption coefficient is higher, that means we have more brown carbon. So we can see that overnight in this time period, we have kind of peaks in the absorption coefficient. We have peaks in the brown carbon. We have peaks in carbon monoxide all at the same time. We also have all of these happening trending along with the PM 2.5. So if we think of our indicators for biomass burning, we have this high AAE for an extended period of time. And we have indicators of kind of high intensity. So we have high absorption coefficient, high carbon monoxide, high PM. But we also seem to have brown carbon being retained during this transport. So we're suggesting that we're seeing this plume from the Canadian wildfire, which would be quite a distance away, but we seem to be having a retention of this brown carbon. So we haven't lost all of that to oxidative processes. We don't, and we can get into the weeds a little bit in discussing across this metro area, we don't necessarily see the biomass burning plume signal the same across all the different sites. And there's additional questions you might ask about how that plume is being transported down to the surface. At our coastal site in Galveston, you can have a lot of influence from sea breeze. So we don't necessarily see all of that. If the biomass burning is aloft, we don't necessarily see all that being transported to the surface. But roughly speaking, in this particular case, we do see that brown carbon. We see that smoke plume impacting Houston at that time. In contrast, if we look at this event that we saw in May, and I'm going to switch sites here for a little bit from Houston to Fort Worth. So Fort Worth is next to Dallas. It's in the northern part of Texas. This is when we had the Aerodyne instrumentation, the Tildes, the HCN. So our BB indicators are a little bit different this time. We actually saw high HCN. And because we had the filter sampler running at that point in time, we were actually able to measure high non-sea salt potassium. We saw high carbon monoxide. The absorption and scattering coefficients were both high, but AAE was only mildly enhanced. This is indicating to us that we don't have a lot of brown carbon associated with that. So we have all the other markers of biomass burning. We have the more inert markers, the less reactive markers of biomass burning for this particular one. So potassium is going to be a kind of a non-reactive marker. Carbon monoxide is going to be a non-reactive marker. And the HCN is going to be less reactive marker. So the black carbon, which would be driving that high absorption coefficient, would also be a less reactive marker. So we're seeing all these conservative markers for biomass burning. We're missing that brown carbon. We're missing that reactive marker for biomass burning. In place of that, interestingly enough, what we actually see are high concentrations of these organic acids. And it's the same organic acids that were reported as oxidation products, long-term oxidation products of the brown carbon. So we're seeing kind of all of these same biomass burning indicators, but in place of high brown carbon, what we're seeing are high organic acids. So we're getting a very different picture from this particular episode. If we start digging in, and I haven't dug all the way in, if we start digging into kind of the conditions that this biomass burning plume encountered, potentially between Canada and Texas, we can see if we do the rainfall and if we do the relative humidity, we can see along the back trajectory, we can see that there are peaks in the relative humidity. So we are seeing that there may be potential indicators of cloud processing happening in this plume. If we look back to see the compounds that we actually have here, we see oxalate, which is a good marker of aqueous processing and a good marker of cloud processing. So what our hypothesis is that in this particular case, we're looking at a more aged BB event, that we have high concentrations of some of these conservative species, high concentrations of organic acids that might be associated with cloud processing. If we look at some of the additional satellite products from Aerosol Watch, we can also see a high cloud density over Texas and in this same region where we see the high AOD associated with that biomass burning plume. So the hypothesis in this particular case is that we're still looking at a long-range transported biomass burning plume, but we're looking at one that's gone through some cloud processing. We can actually see this statewide. So if we look at the filter composition in Houston, if we look at it in Aldine specifically, we can also see this kind of high organic acid concentration during this specific event. In this particular case, I included all of the organic acid data for that year, and you can see that our oxalate concentrations are by far the highest during that June period than they are at the May period than they are at any other time during the year. So we do seem to have this kind of strong indication that we have a very aged and processed aerosol that we're looking at. At the same time, we see peaks in the carbon monoxide, peaks again in the absorption coefficient, but more muted influence on the AAE. So the implications of this, what should we kind of take away from this? These large wildfires may not have consistent impacts on distant sites, We see large differences between the May and the June events. This has implications for how we model the climate forcing associated with biomass burning, how long we model the brown carbon to stay within the plume, how much influence the brown carbon will have on some of that radiative forcing. The implications also are that the conditions during transport, we need to evaluate that more closely. Those atmospheric conditions will potentially impact the aerosol optical properties and the composition of that transported plume. But I would argue then that there is a suite of measurements that we should use to evaluate the impacts or evaluate the impacts and then the composition of the biomass burning plume. So we need to have some combination of conservative species and reactive species so that we can see how aged the plume is and get a better idea of the aerosol processing that happened during transport. I would also suggest that we need iterative comparison with modeling efforts so that we can evaluate back and forth what the potential aerosol processing and environmental conditions, what impact those would have on the chemical composition and on the aerosol optical properties, and evaluate how well we can model that and how well we can measure that. And I think I'm done. I'm a minute and 50 ahead of time, so I think I nailed it. But thank you all. And if you have questions, I think there is a panel discussion. Okay, thank you.
So Road, I think you can start to share your slides.
Yep, there we go. All right, can you see my slides?
We can.
Okay, great.
Thanks. So our next speaker is going to be Rawad Saleh, who's joining us from University of Georgia. He's going to be speaking about how combustion conditions affect the production and physical chemical properties of aerosol. So Rawad, with that, thank you.
Yeah, thank you very much. I'm really sorry I could not be in person with you today, but nevertheless, I'm very grateful and honored by the opportunity to speak to you. So as you probably know, wildland fires can be categorized generally into either wildfires, which occur naturally or unintentionally, or prescribed fires, which are usually ignited intentionally for the purpose of land management. But what you might not know is that historically in the United States, the majority of burned areas were due to human ignition and can be categorized as prescribed fires in today's language. But that trend shifted dramatically over the past century, in part due to climate change, but maybe even more importantly, due to fire exclusion practices post-Euro-American settlement. So now, in terms of areas burned, we have almost a 50-50 split between wildfires and prescribed fires. But with a huge geographic disparity, where the majority of wildfires take place in the West and the majority of prescribed fires take place in the East, as shown by these chemical transport modeling simulations that my student Kritika has recently put together. So these maps show the column burden of organic aerosol that's attributed to wildland fires. And as you can see on the map on the left, in August, which is the wildfire season, the majority of organic aerosol or smoke was contributed by these northwestern wildfires. On the other hand, in March, which is the prescribed fire season, the majority of the smoke was contributed by the southeastern prescribed fires. Now, some of the work that we do in my group is to look at the regional impacts of northwestern wildfires, but I will not be talking about that today because I had clear instructions from Yang to focus on the southeast. So I'll be talking about experiments that we've done to look at southeastern wildfires, wildland fires in general. But before I do that, we need a little bit of background. So, you know, a wildland fire is a combustion process. And when we first learned about combustion, we were taught that fuel reacts with oxygen to produce carbon dioxide and water vapor. And of course, this is the case of ideal complete combustion. And as you can imagine, a wildland fire, the combustion process is far from being complete. So you get a bunch of incomplete combustion products. And the first thing that comes to mind when you think of incomplete combustion is carbon monoxide. But there are other incomplete combustion products that are way more complex and honestly way more interesting. For example, you have volatile organic compounds, and here I'm showing a few examples of aldehydes and aromatics, which are notorious for their toxicity. But even more interestingly, some of the species emitted by incomplete combustion do not like to fly solo as molecules in the gas phase. They like to clump together and form liquid and solid particles that we call aerosols. Now, if you grab a smoke aerosol and look into it, you're going to see that it has some elemental carbon, which is commonly referred to as soot, and some inorganics. And those two together probably make up to 10% of the particle mass. But the majority of the mass is made of organics, which is a very complex mixture of thousands of different compounds. And to add to this complexity, as the fresh smoke is emitted into the atmosphere, it undergoes chemical processing, leading to the formation of more organics in the form of secondary organic aerosol. Now, even though the aerosol mass in smoke constitutes probably like less than 1% of the total mass, it is the most important in terms of health effects. And also, those aerosol particles are very efficient at interacting with visible light, and they are a reason why smoke is visible. So again, even though they make less than 1% of the smoke mass, if you take the aerosol particles out of the smoke, you cannot see it anymore. So to me, and I know I'm preaching to the choir here, aerosols are what makes smoke smoke. And because of this strong interaction with visible light, and as you know, solar radiation, the bulk of solar radiation is in the visible spectrum. This has important implication as to the climate impacts of aerosols, as I will touch on a little bit later. Now, I think you would agree with me, at least intuitively, that the formation of these aerosol particles in smoke, their chemical composition, their physicochemical properties, would probably depend on the combustion conditions that produce them. And this is especially important when we're contrasting prescribed fires and wildfires. So, for the most part, wildfires take place during drought, where the fuel beds are very dry. On the other hand, prescribed fires take place within what's called a prescription window, where the fuel beds are neither too dry nor too moist. So this difference in moisture content between wildfires and prescribed fires lead to differences in combustion conditions, which we hypothesize would lead to differences in aerosol formation and smoke formation in general, which is what we wanted to test in the Georgia Wildland Fire Simulation Experiment, or GWISE, which was an intensive laboratory campaign that was led by my great collaborator, Joe O'Brien, and myself. And we had participants from multiple different universities and national labs. So in GWISE, we performed combustion experiments using fuels collected from 3 different ecoregions in Georgia, from Blue Ridge, Piedmont, and Coastal Plain. Now, the Piedmont and Coastal Plain fuel beds contained surface fuels only. Those are, your pine needles, leaves, sticks that fall and gather on top of the forest floor. Whereas the Blue Ridge fuel bed also contained a layer of duff, which is made of partially decomposed surface fuels that accumulate over decades in regions that have gone long periods of fire exclusion. So we have 3 ecoregions, and then for each of the fuel beds, we conditioned them to 2 moisture contents that are representative of either prescribed fires or wildfires, and then we ended up with this 6 experimental permutations. Now, one thing to note about duff is that from a land management perspective, it is an evil that you have to live with, in the sense that you do not want it to form, but once it does, you do not want to burn it. So prescribed fires, by design, exclude the ignition of duff. However, during droughts, duff can become dry enough to become available for combustion, so it can burn in a wildfire. And because duff has low carbon content and it's very compact, it burns very inefficiently. It smolders for long periods of time and produces a ton of organic aerosol. One notable geographically relevant example is the Rough Ridge fire that took place in 2016 in the Blue Ridge Mountains that kept on smoldering for many days because that region had a lot of duff, and then that produces this thick white smoke that looks very different from the smoke you would see, for example, in Western wildfires. So in our experiments, we wanted to replicate that. So our Blue Ridge prescribed burns, the duff was too moist to ignite, so it did not burn. But our Blue Ridge Wild experiments involved duff combustion, which led to very different combustion behavior, as I will show later on. So we did the burn experiments inside a 1,000 cubic meter burn room. We put the fuel beds on top of a scale so we could measure fuel consumption in real time. And then we would fill the whole room with smoke. And then we had sampling lines that extended to an adjacent instrument room where we did a bunch of different online chemical characterization and physical characterization measurements of the smoke, as well as collected samples for offline analyses. Now, I will not have time to talk about the instrumentation in detail. I will just present some of the results within the allowed time that I have, but of course, I'll be happy to chat offline if you're interested. One thing we did is that we monitored fire behavior using an infrared camera. So we could retrieve what's called the fire radiative power, or FRP. And then we integrated FRP over the course of the burn to calculate fire radiative energy, or FRE. Now, FRE is a function of how hot the fire burned, but more importantly, it's a function of how much fuel you had to burn. So when we normalize that FRE by the fuel bed mass, we get what we call normalized FRE, which we have found to be a very good indicator of combustion conditions. And to illustrate or probably contrast the meaning of these two physical quantities, it is instructive to look at these two experiments right here. So the one on the left is a coastal plain wild burn, which involves surface fuels only. And as you can see, the mass consumption and the corresponding FRE release took place over approximately 5 minutes. And the total FRE was 0.7 megajoules. On the other hand, the Blue Ridge Wild burn, which included duff in addition to surface fuels, kept on smoldering for approximately 2 hours. And because of the high mass loading of duff, the FRE was approximately twice that of the coastal plain burn. However, because duff burns very inefficiently, the normalized FRE of the Blue Ridge Wild burn was approximately 1/3 that of the coastal plain. All right, so my student, Robert, looked at organic carbon, or primary organic aerosol, if you're more familiar with that terminology, and elemental carbon, or black carbon, emissions during GWIS. Robert found that the organic carbon emissions were correlated with FRE, which makes sense because, again, the larger FRE, meaning more fuel had burned, there was more fuel available for combustion, which would emit more organic carbon. And that correlation held for all experimental permutations. Then when Robert looked at the elemental carbon emissions, he found that they were correlated with FRE, but only for the experiments that involved surface fuels only. The Blue Ridge Wild data points, which involved duff ignition, fell way below the correlation. And the reason is that elemental carbon forms in the high temperature flaming phase of combustion and is thus very sensitive to combustion conditions. Consequently, when we look at the ratio of elemental carbon to organic carbon, it was correlated with normalized FRE, which, as I mentioned, is a good indicator of combustion conditions. Now, one outcome of these results that I've just shown you is that we could actually use observations of fire behavior to predict emissions of carbonaceous aerosol. And this has practical applications that I will elaborate on towards the end. My other student, Mohammed, looked at secondary organic aerosol formation during GWIS. And to do that, he sent the smoke emissions into an oxidation flow reactor, where the emissions were exposed to OH radicals to an equivalent atmospheric age of approximately 1 day. And this plot here is for any chemists in the room. Here I'm showing a Van Krevelen plot that maps the organic aerosol molecules based on their oxygen to carbon and hydrogen to carbon ratios. And the takeaway message here is that secondary organic aerosol is made of much more highly oxygenated compounds compared to the fresh primary aerosol, as reflected by these dots shown in green, which are unique in the aged aerosol, having higher O2C ratios compared to the fresh aerosol. But more importantly, what we found is that the amounts of SOA formation in grams per kilogram fuel burned were highly dependent on combustion conditions quantified using the normalized FRE. And the reason is that as normalized FRE becomes smaller, meaning the combustion becoming less efficient, that is associated with more production of VOCs, which are SOA precursors. And if you're familiar with the literature on biomass burning SOA, you probably have noticed that there's a lot of variability in SOA formation and biomass burning SOA formation across different studies. And we believe that our results here provide at least a partial explanation of this variability, namely that it could be explained by differences in combustion conditions across different experiments, because usually these experiments do not control for combustion conditions. We also looked at the effect of combustion conditions on the optical properties of the emitted organic aerosols. But before I get into that, we need a little bit of background again. So a lot of types of organic aerosol, including those emitted in smoldering biomass combustion, are colorless. So when they go into the atmosphere, they act like small mirrors that reflect part of solar radiation back into space, thus cooling the atmosphere. And they are estimated to have a global climate cooling effect of approximately minus 0.3 watts per square meter. On the other hand, elemental or black carbon is very efficient at absorbing solar radiation. And what it does, it heats the atmosphere and is estimated to have a global climate warming effect of approximately 0.6 watts per square meter. Now, wildland fires, in addition to emitting those colorless organics and black carbon, also emit a special type of brown carbon that Rebecca talked about in the previous talk, which we call brown carbon, which is light absorbing, but not to the extent as black carbon. However, we currently do not have a good estimate of the global climate impacts of brown carbon, in part due to the very high variability in brown carbon light absorption properties reported by measurements, field observations, or laboratory experiments. And we don't really have a good handle at representing this variability in climate calculations. Now, the light absorption properties of anything really can be represented using the imaginary part of the refractive index, K. And yes, the refractive index is a complex number. Your high school physics teacher lied to you, and it does have an imaginary part, which is responsible for absorption. Now, for black carbon, being black, it absorbs efficiently at all visible wavelengths. So it has a flat wavelength independent absorption spectrum. On the other hand, brown carbon absorbs more in the blue than it does in the red, and it has this wavelength dependent absorption, which gives it its brown color. This wavelength dependent absorption can be represented mathematically using a power law. So then we could use these two parameters, namely K at 550 nanometers, which is the mid-visible wavelength, and W, that exponent, which tells us about how steep the absorption spectrum is to represent brown carbon absorption. So if you're more familiar with the absorption Angstrom exponent or AEE terminology, W is approximately equal to AEE minus 1. Now, when I started at UGA about 8 years ago, we came up with the hypothesis that brown carbon that forms in combustion is basically undercooked black carbon. And that the variability in light absorption properties of brown carbon depend on the combustion conditions that produce it. So as the brown carbon goes from light to dark, this will be associated with an increase in K550 and a decrease in W up until it hits the black carbon formation threshold, where W will be equal to 0, meaning there is no wavelength dependence in absorption. And to test this hypothesis, we devised this simple laboratory experiments where we would put simple single molecule fuels into a combustion chamber, and then we would tune the temperature and equivalence ratio to create different combustion conditions that would give us brown carbon with different optical properties along what we call the brown-black continuum. Then when we looked at all the data produced from these experiments, we found that they could be represented on what we call K550 versus W space, where if you start from the top left corner, you have very light or low absorbing brown carbon. And as you go to the bottom right, the brown carbon becomes more and more and more absorbing and it approaches the light absorption properties of black carbon. And just for visual representation, this is how these brown carbon particles look like along the continuum when collected on filters. Now, if you're thinking, okay, great, so you've shown that there's this brown-black continuum in laboratory controlled combustion experiments, but what about in real life? So about 5 years ago, I had the opportunity to write a review article on brown carbon. And as part of that exercise, I compiled brown carbon light absorption data from many different studies, and that looked at diverse sources of brown carbon. And I put all these data points on the K550 versus W space. Of course, the data is not as clean as the controlled combustion experiments in the lab, but they tell the same story. And based on this compilation, I suggested categorizing brown carbon based on its optical properties into optical classes, starting with very weakly absorbing brown carbon, weakly absorbing brown carbon, moderately absorbing, and strongly absorbing brown carbon. And to the first order, these optical classes are associated with the sources of brown carbon. So for biomass burning, brown carbon, it mostly falls within the weakly absorbing and the moderately absorbing classes. Now, fast forward to GWISE. My former student, Chase, looked at the brown carbon emissions during the GWISE experiments, and then he mapped them on this K550 versus W space. And something interesting that comes out is that the brown carbon produced from the wild conditioned experiments were more absorbing, had higher K, lower W compared to the prescribed conditions, with the exception, of course, of the Blue Ridge wild burns, which included Duff ignition, which were the least absorbing of all. Now, this clustering of the data told us that brown carbon formation in these experiments were dependent on combustion conditions and could therefore be parameterized as a function of normalized FRE. So as normalized FRE increases, K550 increases, W decreases, meaning that as the combustion becomes more efficient, the brown carbon becomes darker. Now, our ability to parameterize optical properties, emissions of organic carbon, elemental carbon, and secondary organic aerosol formation as a function of these, of FRE and normalized FRE, will enable us to translate our measurements into models. And we plan to do that on 2 levels. So these fire behavior parameters can be retrieved from remote sensing observations. So we could leverage that to apply the parameterizations into regional chemical transit models to improve their performance at representing wildland fire smoke. We also plan to do that at much smaller local scales. So we plan to provide land managers with a tool to predict smoke emissions from planned prescribed fires, so they could use that as a metric for decision making. Quickfire, which you might or might not be familiar with, is a model that's very good at estimating fire spread based on fuel bed composition and environmental condition inputs. And as part of its internal routine, it calculates heat release. So we could piggyback on that to apply, again, our parameterizations within the Quickfire framework to turn it from a model that is good at predicting fire spread into a model that is also good at predicting smoke emissions. And I'm almost done. I mean, but just to wrap up, I would like to bring us back to this question of prescribed fires versus wildfires. If we look at the total amount of aerosols or carbonaceous aerosol formation from our experiments, for experiments, experimental permutations that involved surface fuels only, the prescribed conditions emitted more aerosol than the wild conditions. That's because the prescribed conditions had more moisture content, which makes the combustion less efficient, which produces more aerosol, but not by that much. However, when we look at the fuel bed that involved DUF combustion, under the prescribed conditions, DUF is not available for combustion, but it is under the wild conditions, and that leads to the production of an order of magnitude more aerosol, carbonaceous aerosol, or smog in general. So the implication is that for areas that have DUF, if the surface fuels, which are typically responsible for initial ignition, are cleared in a prescribed fire, sure, that would produce some smoke, but then that would prevent the occurrence of a wildfire that might result or will result with a much more severe smoke episode. And that's all for me. I just wanted to thank our funding sources and GeoWise team. And lastly, just a quick plug-in, GeoWise 2 is planned for this April. So if you're interested in knowing more or even hopefully participating, please let me know and we'll be happy to chat. Thank you very much.
All right, thank you very much. So we'll have our panel discussion towards the end of the session. We were actually thinking of taking a quick 5-minute break, just so everyone has a chance to use the restroom, and also if anyone wants to grab some breakfast, which is right outside. So we'll reconvene in about 5 minutes. So thank you very much, Rawad.
Thank you.
Let me pull up my Yeah. What time is it? Sure. Yeah. Yeah, I'm putting it in my calendar right now. Okay. It's like they do like
How do I operate?
So it's over here.
Thanks for introducing the break, by the way.
Oh, yeah. Just need to exit from here.
What a great session.
I know.
Boy, those are two really good talks.
Yeah.
Then we'll do,
Should be a full screen option.
yeah. Let me see. Oops. Yeah,
There, great.
okay.
Is it shared with,
Yeah, it's already shared. Yeah,
Great.
I can check.
Thank you. That looks good.
yeah.
Yeah, it's already there.
Okay.
What they see.
Okay, great. That's great. And then I just, do this?
Yep.
Okay.
Perfect.
That's fun at that, April 25 field experiment in Georgia. Would he accept, graduate students or undergrads to just like participate? Do you think? I guess I could email him.
Yeah, I was gonna email him because I've been really curious to look at like nutrient profiles and different fuel types being burned. Young and I were just talking about that because people are really interested in it for Everglades management,
Yeah.
right?
Yeah.
So,
Yeah, and it'd be a great experience.
Akita, are you doing the cloud and the storms, right? For the
Oh, that's
climate
the
change,
schedule.
yes,
Okay, so
the
that
third, the
is,
fourth week.
February
fifth.
5th. I was wondering about the dates.
Yeah.
Okay, I need
Good,
to
right?
look at my, I think that's fine. I need to look at my
Okay,
calendar.
it's one day only. It's a Wednesday, 5 to 8
5
o'clock.
to 7.
Yeah,
Okay.
yeah.
Okay.
You don't have to use the entire 3 hours because you're supposed to have the video recorded. So they will watch your video before coming to class.
okay.
Yeah.
Oh, the video of
Yeah.
the,
uh-huh. Whatever
oh,
you
they
want.
come before and
Right.
then we talk about it during class.
During the class, they are going to interview you, right?
Okay.
They're going to ask you questions.
Okay, so it's not like slides or anything. They just ask us questions. and
Right,
we-
right.
Oh, okay.
During class time,
Okay.
during class time. But if you have anything you want them to know before coming to class, you do the pre-recorded video.
Okay.
Okay. The Zoom class.
So let's see that schedule again. So the first,
I'm the first.
and that's next
I have to
week.
check with Helena if this is okay with her.
Okay.
Uh-huh.
So I'm gonna come on I'm out of town next week because
Okay.
of the AMS meeting, but
Yeah, uh-huh.
I will
Helena's week.
come to the next one.
Helena or Young's.
Yeah, I'll come to, I think, I'll come to Helena's
Okay.
and just get a sense of what it's like.
Okay.
To prepare.
Okay. And this is preliminary. I still need to check with everyone.
Yeah. Yeah,
I should have
also
done it
I'm
earlier.
gonna see Helena's too, because the sargassum is huge problem in Barbados.
Oh, yeah.
Yeah.
So
Yeah.
I'm curious to know what it's doing to if it's doing, it should be doing something to the aerosol. I'm kinda
And we
curious
had
to see.
a seminar last semester from
Mhm.
FIU. She talked about a different aspect of the soccer issues. Okay, good. Thank you.
Like your suit.
Thank you.
Snazzy.
It is. All right, everyone, should we get started? All right. So our next speaker is going to be Paquita Zaidama. So she is actually the chair of the Department of Atmospheric Sciences at the Marine Campus. And she'll be talking to us about some field work that she's done looking at biomass burning emissions from Southern Africa. So with that, Paquita.
Right. Yeah, thank you. And really wonderful to be in this session with Rebecca and Rawad. Those were two great talks, and it's also a really nice setup for this talk as well. So I'm going to bring you to a different fire regime, which is Southern Africa and the Southeast Atlantic. There's this image is showing the, bioradiative power dots of fires over the continent. And then you see these LiDAR curtains that correspond to the smoke transported over the Southeast Atlantic, where it goes over a fairly large stratocumulus deck. So it's kind of an area of superlatives. There, everything is large and there's a lot of it. And uh, this motivated, trying to understand this region where we don't actually have a ton of measurements, especially in the post satellite instrument era, motivated 4 campaigns over about 3 years. So there was a DOE mobile facility that was placed on Ascension Island, which is really in the middle of the ocean there for 17 months. And then there were several aircraft campaigns. NASA had one that went back there for 3 months over 3 different years. The UK had one that they based out of Ascension Island, so that was really nice because we had the aircraft profiles on top of the surface-based site in this remote region. And France had a plane that they deployed out of Namibia, along with a surface site that's Henties Bay that was run by Paulo Fermenti. So in combination, we got a very rich data set. And this led us, there's several advantages to this. A main one for us as measurement scientists was that we could compare our measurements and try to figure out what was an instrument artifact and what was real. So because these measurements were made in a remote region, there were like genuine problems with some of the instruments that just could not get fixed in the field. And we weren't necessarily aware of them at the time. We were also trying to relate our measurements to earlier measurements made by a campaign called Safari that was in the year 2000. That was, before the satellite era, it was smaller, but it sort of was the reference data set. And in comparisons to those, we also found differences that we needed to, figure out and kind of agree on. So it was an interesting social process as well. Another thing I want to bring out about this is there were not really any measurements over land except those ones in Namibia where there actually wasn't that much smoke. So we were not really able to definitively connect our measurements to source emissions with as much precision as one might like, as we can do in the US. So that was an interesting challenge to the interpretation of the data as well. But anyway, it's been like, it's totally fascinating area from an intellectual point of view, also relevant. We have collected the articles into the special issue from ACP, if you are interested in delving into it more. Let's see, what did I just do? Okay, so this was the motivation for the experiment, for all these campaigns. It wasn't so much air quality or public health, or as it really was motivated by these discrepancies in the climate model depictions of top of atmosphere radiative balance. I have two circled on there. One is the NASA model that used mirror reanalysis to initialize it, and the one on the bottom is the NCAR model. And I think what's kind of fascinating is these are the two leading models in the U.S., and they are actually spanning the range of the model predictions at this time. So this actually came out of the AERICOM community, these comparisons. So they're about a decade old now, but at the time, I mean, people had some hypotheses about why these were different, but not, it was all kind of speculative. And just to remind people like how it works when you have black smoke over a white cloud deck, or over the ocean, if you have a dark surface, then that smoke is going to cool the atmosphere or our planet. Whereas if you have it located over a bright surface like a desert or white cloud, then that smoke absorbs the sunlight and ends up into a climate warming. And this area in the Southeast Atlantic is where you have the most smoke above cloud in the world. So you get the biggest climate warming signal from biomass burning in this particular region. So I guess I do want to say what my background is I'm not really an aerosol chemist. I've been at UM for 20 years now, and I came as a ship-going observational meteorologist studying marine low clouds. I was really interested in understanding the low cloud processes and their radiative impact. This is from the Southeast Pacific, and I did a lot of work on that area. And through that effort, like the Southern Hemisphere stratocumulus decks really pop out as areas where you get a cooling of our planet. It's those stratocumulus decks are more developed than they are in the Northern Hemisphere. They're closer to the equator, so they bounce more sunlight back to space. So you look at these net cloud radiative forcings, and the Southeast Atlantic pops out as a place with a lot of cooling. But that's a little weird when you think of it in combination with the smoke, because the smoke should be warming. I mean, that should be darkening that region. But despite that, it's still very bright looking from space. So what explains that? And that's kind of what got me kind of passionate about this area, like, what's going on, what's the explanation, and, how does smoke play into this? I also want to reinforce that there wasn't that much known about this area. So I think the first studies came out or that really highlighted the importance, the impact of smoke in this area to the Northern Hemisphere scientists from satellite observations made in the early 1990s or in 1980s, where they had to go to this effort of estimating ozone as a differential in the troposphere, and then releasing ozone sondes from Ascension Island in Africa to affirm that this pollution that they were seeing over the Southeast Atlantic, which was really unexpected because the Southern Hemisphere is the cleaner of the two hemispheres. That's how we normally think of it. So they had to go to that effort to kind of relate the, where this pollution was coming from, that it wasn't from South America, but it was from Africa, and that it wasn't an artifact. So I find that kind of fascinating too, from a history of science perspective. I need to speed this up, I'm sorry. So, okay, lots of smoke offshore. You can see how it's darkening. So you can barely see the cloud deck. Emphasize the difference from the fires in the Northern Hemisphere, which, these are very intense. So Rawad already did a nice job of this. The fires over Southern Africa are agricultural. They're started by people. They're, they are, yeah, there's lots of them. They burn these kind of landscapes so it's dry grass, and that's a very combustible, high intensity fire. But the woods there have become adapted to the smoke over time. So the trees don't actually burn, and these fires tend to just last for about a day or a few days and die down during the night. They're not these, it's not like what's happening in LA. It's kind of managed. It's more, it's just part of the life there. So even though it's an awful lot of carbon that's being released, it's actually not disruptive in the way that it is in the Northern Hemisphere. Okay, I will skip this. So this is a observation that I guess I want to highlight. So from a radiative point of view, the climate models have, they parameterize the single scattering albedo in there, the amount of sunlight that's observed per particle. And a new observation that took us a while to digest was how low, how absorbing the smoke is over the Southeast Atlantic. Not only is that different from observations in the Northern Hemisphere, it also conflicted with observation that had been made during safari. And so that was puzzling. And it probably took about 5 years for people to accept that this really is the case. But this has a big impact on the radiative interactions in that area. Just that plot on the lower left there is just gives you an idea of the net warming that you get just with a change in the single scattering albedo. So Amy Dubrocki is a student who has now graduated, and she's at Brookhaven National Lab, but her thesis was to try to understand why the single scattering albedo was what it was. And I can also mention here that all these campaigns agreed that there's little brown carbon coming off of in this African smoke. So that was also a little bit, well, it garnered a lot of interest. Like, people didn't necessarily believe the measurements, but because all the campaigns found the same result, it's now kind of accepted that there's little brown carbon for, whatever reasons. So that would be, that's still actually a remaining question to try to puzzle that out better. Okay, the grass burns very efficiently, so it releases higher black carbon amounts per carbon monoxide than is normally represented in models. So that's, the Akaji measurements are what are used in the CMIT models currently, and measurements made by oracles by Clarify in the free troposphere indicate higher values. So that would be one reason why you would get a lower single scattering albedo. And the other reason that, and Amy spent a lot of time on this, is that the coating on the black carbon decreases as you go offshore. You lose some of this organic aerosol, and that ends up making the aerosol, the smoke, more absorbing. And I rather like this plot, even though these are not, these are measurements at different places across the South Atlantic. They're not made at the same time, and they're in the same fire regime, but they're not really, it's not really the same plume. But I think it kind of captures that reduction in the coding pretty nicely. And this is supported by work that Art Sedlacek has done at Brookhaven with his SP2 coding core analysis. So the measurements on the far right there are all from the Southeast Atlantic. And they show that decrease with time after a couple of days. So, and this was a nice analysis done by Carolyn Lang, where there was a little bit of single particle analysis that could be done, not too much, but those suggest that the smoke actually becomes more volatile as you go further offshore, like 5 days offshore, which would be consistent with a heterogeneous oxidation process. And this, I think this is my last slide. Just want to highlight that, well, that I thought this was a nice result too. The combustion materials are similar enough over Southern Africa that you can relate the single scattering albedo to this organic aerosol to BC ratio in this region. I don't think that this would apply outside of this region because there's a lot of other similarities in the aerosol that's kind of baked into this that we haven't separated out. But this is kind of helpful for modeling that particular region. We think that you could kind of parameterize this in a model and see what you get. So I think that's yeah, this is my last slide. I thought this might be a nice question to pose to you to end this with, like, of the two leading NASA, leading US models, which of these do you think is more correct based on what you've just seen? And with that, I'm sorry, I did go a little over time. I'll end.
Thank you very much, Pakita. So again, we'll have our panel discussion at the end of the session. So we have one final speaker, and that is Marwa Al-Sayed. So she is coming to us from Embry-Riddle Aeronautical University, and we'll let Marwa take it away. Yeah.
Well, thanks so much, Sandra. And thank you all for the organizers for giving me the opportunity to speak to you this morning. So I'm Marwa Al-Sayed. I'm an assistant professor at Embry-Riddle Aeronautical University, and I'm today going to be talking about work that's in collaboration with EMSL at PNNL. Still we're talking about burning, but we're going to focus on a different type of burning of plastics. So unfortunately, we're all hearing what's happening in LA and the wildfires and how they spread. They have been in the last couple of days. And with these fires, we have a lot of homes that are completely burned out. So our homes are on average made of 20 to 30% of plastics. This could be in the insulation, the plumbing systems, the windows, the flooring, all the construction materials, they have a plastic component to it. But that's not just the plastic burning is not just relevant to wildfires. Also, we have incineration facilities that burn a lot of plastics here in the United States in 2018, which is quite recent. A total of 5.6 tons of plastic was incinerated. This is 16.3% of the total municipal solid waste in the United States. This is data according to the United States Environmental Protection Agency. But also in developing countries, we have open burns. So in India, for example, 5.8 million tons of plastics are being burned in open air each day. So what does this mean? What does it mean for the emissions and the pollutants that are coming out of these burns? So really the goal of this study was to look at those emissions and characterize both the primary as well as the secondary organic aerosol that's emitted from plastic burns. We did this through experimental study. The location of the experiments took place on MZL campus at PNNL in the summer and fall of last year. Still living in 2024, hard for me to think that this was last year. So it happened in 2024. And this was a part of the experiments were part of a bigger campaign called SMOKE. You see on this figure here, this is the diagram showing the experimental setup of the combustion chamber. We looked at two types of plastics, polystyrene and PVC. And the reason why we chose these two plastics, because they are prevalent when it comes to the plastics that we use in construction material, as well as the materials used in houses. The combustion temperature was set at 600 degrees Celsius. The emissions coming out of the combustion chamber were collected in two Teflon chambers. The first chamber, Teflon chamber number 1, collects the primary organic aerosol. So all the emissions coming out in the aerosol that's directly emitted from combustion is collected in that chamber, while in the Teflon chamber 2, we filter all these aerosols and we collect the volatile organic compounds that are being emitted, and then oxidation reactions using ultraviolet and OH radicals happen in that second chamber. And then both of the collected samples in both chambers then undergo a series of offline and online characterizations for morphological as well as chemical characterizations. So let me first, I just want to emphasize that this is still work in progress, and this is preliminary data, but it's very exciting. And I hope you get as excited as we were and as I am with the results. So first I'll walk you through what these emissions look like. So this is data from the scanning electron microscope. On the left figures, you're looking at polystyrene results, both the POA and the SOA. And on the right panels, you have the PVC results. So for the polystyrene, POA, and SOA, we saw that they are very flat. And what this means is that they are liquid-like. And the same results you can see for the PVC SOA, or the SOA formed from PVC burning. Still, it's flat. The particles are flat, meaning that they are liquid-like. However, when you look at the results for the POA PVC, now they are very different. They look very different. And they actually look like a morphology of what we see for tar balls. So this might actually have implications. Climate implications or data forcing implications. Still, it's a question that we're trying to address in future experiments. So what are these particles made of? So with the computer controlled SEM with EDX, we saw that on the left for the POA from polystyrene, it's mostly CNO. Particles are CNO. But then for the PVC PO, we now start to see CNOCl. So we start to see chlorine-containing compounds. And this is for the primary organic aerosol. While we don't have the same results for the SOA, we have different SOA results using the NanoDesi So this is data from the NanoDesi for the secondary organic aerosol on the left for the polystyrene and the figure on the right for the PVC. And you see that the green color is the CNO and the CHNO is blue, and the SOA from polystyrene contains these two compounds. However, the SOA from PVC starts again we start seeing chlorine containing compounds, and we saw at least 5 different types of chlorine containing compounds with the secondary organic aerosol that's formed from PVC. So now let's look at individual particles. These are results from the mini split of ALA and MZO. And on the left, it's results for the polystyrene POA. And on the right, in green color, that's the polystyrene SOA. And in both cases, we see high fractions of high molecular weight compounds. And these include PAHs, so polyaromatic hydrocarbons. And also for the POA of polystyrene, we saw elemental carbon. In terms of the shape, both were spherical, and the density for the SOA from polystyrene was a little higher compared to the density of the POA from polystyrene combustion. For the PVC combustion, again, chlorine-containing compounds for both POA and SOA, and again, in terms of dimensions and morphological shapes, they were spherical, but their densities were comparable. So really the key and most exciting point that I want to convey here is the fact that we did observe new particle formation. Remember, the Teflon chamber number 2 did not have any particles to start with. So any SOA formation that was generated in that chamber was actually, there was no pre-existing aerosols. So this is evidence for new particle formation. And in terms of mass loadings, the mass loadings for the secondary organic aerosol formed from polystyrene was in 1 order of magnitude higher in comparison to the SOA from PVC. So let's talk about the volatility of these compounds. How volatile are they? So that warranted the investigation of the evaporation kinetics of both POA and SOA from polystyrene and PVC. And on the left, you see the kinetics and the evaporation diagrams for polystyrene. There's evidence that we have a low or none volatile compounds, specifically for the secondary organic aerosol. 83% of the SOA from polystyrene was non-volatile. And in the case of PVC, the non-volatile compounds made an even higher contribution. Most of the SOA that's resulting from PVC was non-volatile. Implications for cloud formation and ice nucleations and impacts on the Earth climate. So we had to look at the ice nucleation properties of these compounds, because there's no literature about it, because this hasn't been investigated before. So this diagram is the ice nucleation efficiency for PVC. On the x-axis, it's the ice saturation ratio, and on the y-axis, you're looking at the active fraction. So, and the POA is shown in red color, and the SOA is shown in green color. So let's look at the ice saturation ratios between 1.2 and 1.4, what's happening there. As we increase the ice saturation ratios on the x-axis from 1.2 to 1.4, we don't see much increase in the green color pertaining to the SOA PVC, which indicates that the SOA from PVC is likely very weak ice, has weak ice nucleating properties. However, the POA shown in red now is enhanced as we enhance the ice saturation ratios. And what this shows is that there's now there's evidence that the SOA from PVC, or excuse me, the POA from PVC has very strong ice nucleating power. So take home messages. Well, first and most important is the evidence for new particle formation. And that means we need to include this, these pathways for the formation of SOA in chemical transport models, because currently this is not part of any of the chemical transport models. The emissions from PVC that contain chlorine-containing organic compounds, these have implications for the ozone layer and for the chemistry in the ozone layer and affecting the ozone hole in the stratosphere. Also, the ice nucleating properties efficiency, they can improve the predictions of aerosol cloud interactions. So we need to take those into consideration when we're looking at global models and radiative forcing impacts. Finally, the low volatility and the high molecular weight of aerosols, whether they're from PVC or from polystyrene, they suggest that we need to update those properties in whether they're aerosol optical properties or thermodynamic properties in our models. So like I said, this is still, we're running more experiments. And in the future, we're hoping to look at the biomass burning in addition to the plastic burning and see what happens when we add both together. So not just looking at the plastic burning, but also adding the contribution of biomass to it and seeing in those mixtures, how will these properties change for plastics and how those will also affect the properties of the biomass that's being burned itself and the emissions from biomass that's being burned. By that, I would like to thank AmCell for funding this work through their Exploratory Research Award earlier this year. And also, I would like to thank Embry-Riddle Aeronautical University for partially funding this work through their faculty professional development program. And I would like to take any questions in the, I guess, in the panel discussion.
Thank you very much. So I'd like to invite all of our speakers to come up front for our panel. So we'll open questions both in person as well as over the Zoom. So if you're on Zoom and you have any questions, feel free to raise your hand and unmute yourself. And yeah, we'll start out our discussion.
I have a question about maybe I can speak to the mic. So I have a question regarding the aging of the smoke, right? So I think in Rebecca's slides, you showed that the cloud processing will influence or sort of promote the aging. So do we know the time scale for this process? And also I think in Paquita's slides, so we don't see much of the brown carbon at Ascension Island. So is it possible that maybe cloud processing is playing a role in the observation at the LASIK campaign? Yeah. Yeah. No.
I think that's a great question. I think I had references in my slides. And I think that the Hems and Abbott reference does discuss kind of at the fastest, if you have like 100% aqueous processing, I think it can happen as fast as 4 to 12 hours. So you can have it, if you have kind of continuous aqueous processing, if it's just photolysis, it's significantly longer. So if you don't have aqueous processing, then the brown carbon lasts significantly longer. I think it's entirely possible if the biomass burning plumes coming off of Africa are multiple days old already, then you could have potentially had some of that cloud processing happening already, especially in such a cloudy region. I do, if I can also just say that the combustion conditions may also be promoting more black carbon than brown carbon, if it's the grass fires, like you were saying. So I think that also may play a role in some of that as well.
So do you think that grass fires just emit less brown carbon? Mhm, mhm.
So if you have high temperature.
Can I jump in here for a second?
Yes. The voice of God, but yes.
Yeah.
Yeah.
Yeah, so the way I do think about it is, I wouldn't say more or less brown carbon. I mean, brown carbon is kind of, it's either dark or light, and brown carbon is not that one thing. So and I think I look at it as organics, and whether these organics are dark or not dark. So for grass fires, yes, they take place, the combustion at relatively high efficiency compared to other biomass, and they emit higher black carbon compared to organics. But these organics that are emitted from these high efficiency fires are more absorbing. They're darker than the ones you would get in, say, smoldering combustion. But they get emitted at smaller quantities. And a lot of times, depending on the measurement technique employed, they get lumped with black carbon because their light absorption properties get closer to those of black carbon.
That's a really interesting perspective because we have been struggling to reconcile how it can be that it seems like there isn't much brown carbon. So maybe that we are kind of miscataloguing it a bit. I'll have to go back and see if we can puzzle that out with what we have. I did want to add that the aircraft measurements are mostly in the free troposphere, so there's no cloud processing, and that's really a lot. Yeah, I think what I showed was mostly from the aircraft. Aqueous processing on the island, we have not been able to distinguish that from differences in the sources. So there's more sulfate earlier in the biomass season when the smoke is also spending more time in the boundary layer. So to me, that suggests that there is aqueous, and also the aerosol size distributions suggest it. And it's also more efficient than, or it's quite efficient. But we don't have definitive markers. We don't have the oxalate. We don't have SO2, so we can't do a closure. So I think this would be a great topic to go back and try to be more precise. And another reason to do that is because there's a major shipping lane that cuts across the Southeast Atlantic, and a lot of people interested in marine geoengineering have been focusing on that shipping lane as a example of how much shipping can influence the cloud properties there. And I have to keep wondering how much sulfate is from background conditions from smoke, because once, as you know, the smoke tracers stay in the boundary layer for a long time, and they actually accumulate during the season so that the whole background level increases throughout the year. So anyway, good proposal fodder.
Could you come up to the microphone?
So this question is for Rawad. I was interested in the brown carbon to black carbon continuum. Similar thing. What's the time scale and what factors influence it, and how much would it change that timeline?
You mean for formation and combustion?
Yeah, the brown carbon to black carbon continuous continuum. The time,
Mhm.
like what time scale are we looking at and what factors affect it?
Yeah, so it's really the combustion condition. So if you think of a combustion process, I mean, if you ask a combustion scientist, which sometimes I pretend I am, they look at a soot formation route, what they call the soot formation process route, where as the temperature of the combustion becomes high enough for the formation of the first aromatic ring, this is the beginning of the soot formation process. And then as the temperature starts to increase, then the thermodynamics favors the accumulation of these rings into making larger and larger pHs, which of course can have other functional groups on top of them. But eventually, if the temperature becomes high enough, then they undergo carbonization and they lose a lot of their hydrogens, and that's what marks the formation of elemental carbon or black carbon. So really, it depends on the combustion conditions in terms of temperature and air to fuel ratio, and how long the combustion takes place. I mean, if you put something and burn it for a long time, it's a chemical reaction. So all these three things play a role. So for something, maybe it's interesting to look at it from a very different perspective. If the combustion is very efficient, then you won't make anything. You won't make no brown carbon, no black carbon, nothing. You just convert everything to CO2. And now you step back in terms of efficiency from that, you start to make black carbon because it is very stable at high temperatures. And that would be, for example, the case in a diesel engine, where the combustion is not 100% efficient, but it's designed to be efficient because you're trying to extract as much energy of your fuel as you can. And then if you take a step back from that, if you look at biomass combustion, which is less efficient than in an internal combustion engine, then you start to make a lot of organics, and these organics are now dark brown organics, something like a grass fire. Then take a step back from that, you're looking at the experiments that I was showing a little bit earlier. The combustion is less efficient. It makes more organics, less elemental carbon or less black carbon, but those organics are not as absorbing. And then you can go to DUF, which is the least efficient combustion on this biomass burning spectrum. Now you're making a lot more organics than elemental carbon, but those are very weakly absorbing. Does that answer your question?
Yes. So I had a question for Marwa. I was really interested in some of the PVC results, especially the chlorinated containing compounds. So there's been some recent work that has suggested that HCl emissions potentially from plastic burning is an important component in some of the hazes that you get in parts of India. And also, we do a lot of halogen chemistry in my lab, and one of the conundrums that we have is where are the sources of inland chloride coming from, so away from the ocean. So I was wondering if you could comment a bit on the PVC as a chloride containing aerosol source, as well as if you have any insights from the gas phase about any emissions that resulted from the PVC combustion.
A great question, and I saw it coming from you, Cassandra. So definitely what these results show that now we can have a better understanding of where the Cl compounds or the particles that we see inland. So it's not just the sea spray that's the source of Cl anymore. In areas where you have open burns and wildfires, you're going to see Cl containing compounds as well. So what we're actually working on right now is, can we use any of those as markers, specific markers for Cl from plastic burning in comparison to Cl, from sea spray. In terms of the gases, we're actually running some more experiments to look at the gas phase and the VOCs, because that will give us a completely different insight, you know, not just the particles, but also what they start from, especially for secondary organic aerosol. So it's a work in progress, and we actually had a meeting last week of those VOCs and gas phase characterization. But thanks for bringing it up. Yeah.
I also have a question about the plastic burning process. So you mentioned it's liquid lag. So how that happens? So does the plastic melt first and then they gasify and then they reform them like a small particles, or they just melt it and then throw it to the air and then finally become small particles?
So good question. Thanks, Javier. So this is not at high temperatures anymore. The collection in the Teflon chambers is at ambient temperature. So we're definitely the liquid like is not because of the melts, because these are the emissions from the plastic. So they're not even plastic compounds anymore. They're organic aerosol, whether primary or secondary, depending on which chamber is being characterized. Yes. But then since past the combustion chamber, the temperature is no longer, is just ambient, it's no longer 600 degrees. So it's not a molten solids, it's rather the morphology of the particles. And all these are particles, so aerosols. Yes, yes, yes. Of course.
My question may be outside of the box for the panel over here, but I just wanted to pick your brain. How much you have learned from the outdoor burning can be applied or translated into indoor burning, for example, incense burning or solid fuel burning? Thank you.
I think there is a lot of overlap. So in terms of, there's literal overlap between outdoor burning and indoor burning, because you can see, I think Yuste Gao recently did a study in Colorado showing the impact and influence of these wildfires on homes that don't get burned. So you can have a lot of that smoke then partitioning into the surfaces in the interior of homes and then off-gassing over a long period of time. So you can have that kind of indoor-outdoor confluence in those particular cases. Definitely, if you're looking at specific burns, you will see some of the same gas and aerosol composition coming out of some of these kind of candle burn. So there's been candle burning studies and incense burning studies, and sometimes religious or church environments will have a lot of incense burning. And so you can have a lot of kind of emissions associated with that would have then impacts on human health and exposure and those types of things. You start then, if you're talking about indoor combustion, then you start going into cooking a little bit, right? And so there is a lot, it is gradations in there. So you can apply some of these basic concepts. If we go the reverse direction and go from indoor to outdoor, so some indoor sources become important for global climate, right? So if we have residential burning, that then is important in terms of black carbon and brown carbon emissions into the atmosphere. So yeah, I think you can apply some of those same kind of methodologies to studying indoor and outdoor.
I can jump in for a bit. That this is, I agree totally, Rebecca, this is true. I mean, the same techniques can be used for for analyzing indoor combustion, domestic burning, if you will, as to open biomass burning and wildland fires and grass fires, etc. And just to place it back, so our idea is using this combustion conditions as in a way, a unifying parameter that we can put different combustion processes on it, and the domestic burning and solid fuel burning would be more efficient than in a wildfire or prescribed fire. So it will produce typically more black carbon compared to those fires, and less organics, but will be darker. And we have some measurements to look at that. Of course, there's a difference between when you're using that, because you're trying to extract, again, the energy out of the fuel for cooking. But then when they're left out to smolder, then they turn into very inefficient combustion, and they will now emitting more organics, would look like white smoke coming out of them.
Thank you. I'm Nusrat Jung from Purdue University, an assistant professor. Thank you, CY, for setting the stage for our 2:00 session, where we will talk a lot about indoor emissions and what happens when you have an episodic event. I thought to ask a question about the chemical disasters that are occurring all across United States, also in the world. There was a recent train derailment in Ohio, East Palestine, and we were involved in doing some work there. There was a controlled burn situation, about over 20 train cars just simply derailed. They were full of chemicals, and the best solution they could think of at that moment was to actually burn all of this. So they burned all the chemicals in a very, rapid manner, and I'm not sure what kind of thinking really goes in this kind of event, because when the event happens, everybody comes together to make decisions. Is first the local authorities, and if it is too big of an event, federal agencies get involved, and before anyone can be informed or any testing can be performed, decisions are just simply made. So when you have a situation of a controlled burn of extreme amount of chemicals, it did produce huge amounts of pollution that was carried over. So my question is, what are your thoughts about, characterizing this and making these incidences part of your studies? And how do you observe, when you observe data and, do your studies, what kind of information is available on these incidences? Are they recorded? Does it happen? Is someone really doing work in that area? Because they seem to be really increasingly prevalent. It's too out of the box question.
So I'm from Texas, and Houston, Texas has a lot of these types of events. So you'll have a explosion of a storage tank of fuel. Was it the Discover Horizon? The big oil spill that happened out in the Gulf, that was also the solution at that point in time, was to burn the oil slick on the top. And so we have thought about that a bit. How do you address some of those, characterizing both the human health type of questions, and then in terms of the chemistry, understanding what those potential impacts are. And I think that the strategies that we've discussed in Texas are a combination of what do you need to have at local monitoring sites to cover kind of that full spectrum. And so often you'll have PM, you'll have NOx, you'll have ozone. That doesn't really cover a lot of your chemical burns. And so a lot of times that the information that you get out from the state agencies or the federal agencies we don't have a problem in terms of our EPA criteria pollutants. And that usually doesn't cover a whole lot. So VOCs aren't typically covered in that. So this may be where something like total VOC sensors would be more relevant in terms of having a wider network of those available. The other thing that we have discussed is rapid response. And so the state or someone having a rapid response vehicle that has more elaborate instrumentation, that has kind of VOC capabilities or maybe aerosol characterization capabilities, filter samples. I always think of filter samples or cartridges as being an archive potentially of contaminants. And so making sure that in our era of real-time instrumentation that we're also doing some of these archival type samples, so having filter samples collected. But I think it is some combination of making sure that our monitoring sites basically have a wider spectrum of pollutants covered. So we need to have more VOC information. And then also having rapid response. A academic institution can't necessarily muster up fast enough. You might be, if you are really fast as an academic institution, you can maybe respond in a week or two, right? That would be really fast. That would be impressive. But you need to be faster than that to be able to respond to some of these types of situations. And so I think that would be that's kind of the thinking that I've done on that has been in those type of directions, that we need more sensors, so we need more monitoring that we can do cheaply and continuously to catch things. And then we also need more rapid response.
So in particular for the Ohio case, there has been evidence that there's vinyl and the question of BVC burning and what it means to the, to the emissions associated with those burns. So there's actually a study out there that documented that. But the problem is we need research to understand that burns are not, incineration might not be the solution. And what conditions should we burn at, right? So Rawad mentioned there's a lot of variability in literature, and their variability is because the combustion and the burning conditions are changing. And I just want to emphasize also that replicating these experiments is not an easy task. So when you're running a combustion chamber and you want to run it again, you're not necessarily going to get the same exact results. So that's another thing that we run into with these experiments and in this field of burning. But research needs to happen to understand what are the implications of burns so that we can take it to the next level, to the politicians, to, on a local level, on a state level, even federal, if we want to include and we want to advocate for VOCs added to national ambient air quality standards, then we need to have evidence for that, right? And that's not going to happen without the fundamental research that's we're conducting in the community, if that helps.
So I have a question that can probably bring people back to the box of biomass burning. So more specific to Rawad. So you use this FRE to indicate combustion efficiency. I think quite many people also use this modified combustion efficiency. It's like CO and CO2. And people also say that in field observations, this modified combustion efficiency can have a wide range. I don't know, for your FRE, do you expect to have wide range in your experiments and actually also in the field? And how do these parameters correlate with each other? And another question is, I think trying to bridge what happens in the lab and in the field. So people also have found discrepancies in this mass enhancement ratio of the photochemical aging, right? So in the field, it seems like the enhancement of the particulate mass is not that significant, but in the lab, there's more mass being produced. So I don't know how we can address this issue there. Yeah.
Just before, so for your second question about, can you say that again? Mass enhancement, or are you talking about the
the mass
enhancement
enhancement due to the photochemical aging?
Okay, so the increase on aerosol mass. Sorry, I keep.
Yes, yes, that's right. Yeah.
Yeah. Yeah, so these are two great questions. For the first one, so for just to bring it back, so FRE itself is not an indicator of combustion conditions because it's the total energy released from a fire. So if you have a big fire, you will have a high FRE. If you have a small fire, you will have a small FRE. So it just tells you it's a combination of combustion conditions and how much fuel was burned. But the parameter that we came up with is what we call normalized FRE. So when we normalize that by the fuel bed mass, and then you will have an intensive kind of property in energy per unit mass. So this is what we use to characterize combustion conditions. And yes, it will be correlated with the modified combustion efficiency. The high normalized FRE would have a higher modified combustion efficiency. But the thing with modified combustion efficiency, and I don't know if anybody is a big fan of that parameter. I hope I'm not offending you, is that it is not very good at predicting intensive property, at least in my field, specifically optical properties. So if you look at the optical properties of the aerosols, there's kind of usually there is a very flat dependence, and then suddenly it becomes very steep on modified combustion efficiency. It does not kind of resolve that parameter space very well. One thing that we found would be a good, for example, indicator of brown carbon light absorption properties is the ratio of black carbon to organic aerosol. That would be a better indicator. But both of these things, whether it's the black carbon to organic aerosol ratio or the modified combustion efficiency, are observations that emerge from the combustion process itself. So we're trying to take this a step back to fundamentals and look at the combustion process itself. If we can look at it, characterize it very well, then we can be able to predict those emissions.
Thank you.
Yes. For the second question, I would say it is because of the different combustion conditions that whatever experiments that were done in the lab versus I'm not familiar. I mean, you might. I know there's a lot of variability in the enhancement, organic aerosol enhancement across experiments, but I was not very aware that the bias is lab measurements versus field experiments. It could be. I would definitely relate that to differences in combustion conditions, at least. At this point, it's more of I cannot. I mean, I will need to look at the specific studies to link it to that, but I think it is definitely related to that, at least in part.
Sure. Thank you.
All right, so I'm hoping to get a question either from a student or from a Zoom participant, just to mix things up.
My question was about the plastic burning. So you talked about how the primary organic aerosol from the polystyrene was mostly like CHN compounds. And I was wondering, where is the nitrogen coming from? Like, what is the chemical processes behind that?
Question mark. The same question that we still have. So, well, there's nitrogen requires, higher temperatures to, to break the bond, right? Higher than 600 degrees. So the question is that we're trying to investigate now is where does the nitrogen come from? I mean, it's a little bit, but still it's there. But good point. Thanks for capturing it. And it's next year, I'm going to have an answer to this.
Any more questions from Zoom participants or from any students in the room? Or anyone else? All right. All right, well, I'd like to thank then all of our participants, all of our speakers for a really wonderful and thoughtful session. And now we'll convene for a break and then for lunch. Yeah, and then we'll come back at 2 p.m. for our indoor air quality session. So thank you.
Thank you very much. It was great. I definitely learned a lot from the other talks, and I'm really, again, it's kind of, we had the one snow day that happens one every 3 or 4 years here in Georgia happened to happen today. So it was very unfortunate that I could not be with you in person.
Yeah, sorry we miss you, but next year, feel free to come by. Yeah, thank you.
Good afternoon, everyone. Welcome back to the final session of our workshop. And the final session is about indoor air. I remember one time I was talking to the NSF Environment Engineering Program Director, and he was asking me, what is the most hot topic in the air right now? I was thinking all different kinds of directions. And then his answer was indoor air. That's the hot topic for air quality version. Okay, so we are very happy to have this discussion over here on indoor air. And the first one, we are going to have Professor Brendan Bohr, who is Dr. Marjorie Hoffman Associate Professor in Civil Engineering at Purdue University. And Dr. Bohr is an expert in indoor air, of course, and in terms of nanoparticles, exposure, assessment, and the different applications. So let's welcome Professor Bohr.
So thank you, CY, for inviting me to the University of Miami to present on some of my indoor aerosol research at Purdue University. I've been there for about 9.5 years now, studying nanoparticles, bioaerosols, and so forth. So this talk, I'll highlight some of our ongoing research on indoor nanocluster aerosol dynamics. So these are very tiny ultrafine particles that are present in the indoor atmosphere and come from a variety of sources. And I'd like to touch on some of the measurement and modeling considerations, just as kind of provide some guidance if you are planning to do some of this type of research. Oh, okay. Nope. So nanocluster aerosol, or NCA, is the acronym. These are very small nanoparticles. I believe this is a relatively new term that has been used in the literature, and these are particles smaller than 3 nanometers in size. There's been a lot of work, I would say, with respect to new particle formation in the outdoor atmosphere as well as combustion, and looking at the presence of nanocluster aerosol, their size distributions, their concentrations, and measuring them to look at aerosol nucleation processes. There's been some work looking at measurements of nanocluster aerosol near roadways, emissions from vehicles. Concentrations can be elevated, and they're certainly elevated when there's an atmospheric new particle formation event. Measuring these particles provide a basis to calculate nucleation rates, formation rates, and growth rates of very small particles. Indoors, much less research has been conducted. Our group has published a number of papers on nanocluster aerosol and a few other groups as well. And what we're seeing is that there's many sources that can produce these very small particles, whether through direct emissions from combustion sources like gas stoves, which I'll discuss in this presentation, or through secondary processes, particularly related to the ozonolysis of monoterpenes, which are found in many scented fragrance products, as well as the ozonolysis of skin oil. So just ozone reacting with your skin can produce nanocluster aerosol. I believe these particles are important for a variety of reasons. One, measuring them provides us a basis to understand emission dynamics, nucleation and growth dynamics. I believe they're important from a health perspective because of the high deposition fractions of these small particles in the respiratory system, which you can see in our deposition fraction plot here. So very high deposition, of course, in the head airways, but also in the tracheobronchial region. So the maximum for the tracheobronchial deposition curve is about 4 nanometers. So there can be a significant body burden of these very small particles. They're very difficult to measure using a variety of different differential mobility analyzers and condensation particle counters. Those type of instruments are a little bit difficult to bring to the field. So they're more for laboratory-based measurement. So we really don't have much data on the indoor abundance of nanocluster aerosol, the concentrations and the size distributions. One possible major source, at least here in the United States, are gas stoves. And I'll discuss that in my talk today about the production of nanocluster aerosol from a conventional gas stove, the dynamics of these particles once they're emitted to the indoor atmosphere. So I'll highlight both how we can measure these particles and how we can address them through mathematical modeling. So with respect to gas stoves, I think this is something that has received a lot of attention in recent years. This is by no means a new source of indoor air pollution. I think it's been very well studied. And there's been a lot of dialogue in the United States about the impact of gas stoves on human health. And some of this has become a little bit politicized, but certainly I think anybody that studies indoor air quality would tell you that gas stoves emit a lot of pollution. This is probably something we should move away from. There's been some nice studies looking at linking the use of gas stoves to childhood asthma. One is shown down here. It's about 12% of childhood asthma can be attributed to gas stove use in the United States. And this kind of prompted some discussions in the past 2 years about potential ban on gas stoves in different states throughout the United States, New York and Chicago, Illinois. This really hasn't made too much progress. I think there was some discussions at the federal level resulting in this headline, Joe Biden is not coming for your gas stove. And I would probably say neither is Donald Trump. So I don't think gas stoves are going to go away anytime soon. Americans love their gas stoves. And because of that, we want to have a better understanding of the emissions from these ubiquitous sources. So one additional study that was just published last year in Science Advances looked further into the health outcomes associated with gas stove use among low-income and disadvantaged populations in the United States. This is both gas and propane stoves. And I think they provided us some good evidence that gas stove use is driving an increase in childhood asthma. They linked it to 50,000 cases, and that was linked directly to the nitrogen dioxide exposure that was occurring. And that's very helpful, and certainly NO2 is a pollutant that we should be measuring indoors and certainly coming from the combustion process. And they found that the concentrations are often above exposure limits. But they included one quote in this article that I found to be quite helpful, is that we know that gas stoves and any cooking process is emitting a wide variety of pollutants in the gas and particle phases. They talk about carbon monoxide, benzene, formaldehyde, and then I highlight there in red ultrafine particles. And I believe that, you know, when you're cooking on a gas stove, you're inhaling a relatively complex mixture of pollutants from the combustion process itself, also from the cooking process. And I think that some of these other constituents are part of the puzzle and maybe it's driving some of these adverse health outcomes that have been reported. So this study was just looking at NO2, and I think that, as they note, they are underestimating the health consequences. I think if we were to include ultrafine particles, you know, maybe we'd have a more complete picture on the impact of these stoves. So in looking at cooking indoors, I think it's important to understand that even if we move away from gas stoves, we're still generating a lot of indoor air pollution when we cook from the high temperature cooking process. So even if we move to an electric induction cooktop, cooking will still be a major source of pollution indoors. So we have to remember that. And that the emissions from the combustion process will interact with the emissions from the cooking process. So with respect to gas stoves, we can have propane or methane. In Indiana, where I'm from, there's a lot of rural properties where they have propane tanks, so they're using propane rather than methane. One, I think, aspect here is you would think, well, just turn on the kitchen hood. Of course, that's a good solution. Problem is a lot of people don't use their kitchen hood when they're cooking with propane or methane. Some studies have looked at maybe about a third of the time people actually turn on their hood, which is vented to the outdoors when using a gas stove. So a very obvious solution that is not like really widely implemented or adopted. So when we're cooking, we're producing many different types of pollutants in the gas phase, of course, combustion products. One thing there to highlight with respect to the cooking process especially is the production of a wide array, diverse spectrum of volatile and lower volatility organic compounds that are produced from cooking with butter, oils, and other fats, and so forth at high temperatures. And there have been more and more studies in recent years characterizing organic compounds and their production from cooking. So you have all that being emitted in the gas phase. In the particle phase, of course, we have particles in different size fractions. And I just want to note the ultrafine particle size fraction within which we had the nanocluster aerosols, which are below 3 nanometers. So with ultrafine particle measurements, these have been made indoors when people have been using gas stoves. More commonly with condensation particle counters that are field portable, so going down to about 10 nanometers or so, sometimes a bit smaller, but generally we're not measuring these very small particles down to, let's say, a nanometer, a single nanometer in size. So we really don't have a complete picture on the particle production and associated dynamics when using a gas stove. And because we're producing a lot of lower volatility compounds when we're cooking on top of the gas stove, we could have a lot of interactions between the gas and particle phases. So condensation of some of these lower volatility species onto the particles that are produced from the combustion process. So when you start cooking, it's a pretty complex process, and the nanocluster aerosol just one component, but I think something that certainly warrants attention. In looking at how to measure nanocluster aerosol concentrations and size distributions, what has been commonly done outdoors is using this AirModus particle size magnifier. This was developed at the University of Helsinki in Finland. So this is using diethylene glycol to activate these very small particles. And then they're sent typically directly to a condensation particle counter, often with butanol. And that has worked very well to measure these particles outdoors, where concentrations are generally not that high compared to what we see indoors. And the size distributions are not changing very rapidly. So looking at kind of slow nucleation and growth processes. But that particular combination of the PSM particle size magnifier and the CPC from AirModus has generally worked quite well for the atmospheric measurements. We are fortunate to work with Grimm, with Gerhard Steiner at Grimm in Germany. And they have commercialized a product that takes one of their DMAs, SDMA, Differential Mobility Analyzer, and then pairs it with the PSM from AirModus and then uses one of their CPCs along with their X-ray neutralizer. And they call this new product a PSMPS, Particle Size Magnifier Scanning Mobility Particle Sizer. This is something that is now commercially available, so you can purchase it. We used it on a loan from Grimm, and now we have purchased one at Purdue, and I have to say it worked very well for our measurements. So a few considerations here for our study was the presence of the charger ions from the neutralizer. So this is something where the charger ions can interfere with the measurements, but you can look at it a different way. Due to this particular configuration, we saw a very nice baseline concentration of charger ions, and that gave us a diagnostic tool that the instrument was more or less working correctly because we could see the charger ions from the neutralizer. We knew that we were able to both size classify these particles with the DMA and then activate them with the PSM and detect them with the CPC. So it's a very good diagnostics tool for us when doing the measurement. The only issue is that since we're trying to measure these nanocluster aerosol and they overlap in size of some of the charger ions, generally below 2 nanometers, we had to do some corrections for the presence of those charger ions. But we were able to handle that, and I think overall it worked quite well. With the DMA, we get very good size resolved information beyond what you would get with just using the PSM by itself with the CPC. Where there's a rather crude way of figuring out the size distributions by changing the saturator flow of the diethylene glycol. So with the DMA here, we were able to get pretty good size resolved information of these nanoparticles. In this case, this new PSMPS provides data from about 1.18 nanometers to 52 nanometers or so in electrical mobility diameter. And we were very happy with it. We did not take it to the field. It would be a little bit cumbersome to do so because there's some pumps involved to operate the PSM, but generally was quite helpful for our measurements. So we did the measurements in a very nice facility created by Dr. Nusrat Jung at Purdue called the Z-Edge Test House. So this has become our basically indoor air quality chamber at Purdue, where we can do some realistic residential activities. What is nice about the facility is that when we use some mixing fans inside of it, we can create a well-mixed environment. And then that allows us to apply a well-mixed reactor model to evaluate the dynamics of different types of air pollutants. So this is a mechanically ventilated space, has its own kitchen, a bathroom, a living area. And basically what we did is we used a loft where somebody would foreseeably put a mattress to sleep to house some of our aerosol instruments. So we had up here a PSMPS, and since the data only goes up to about 50 nanometers, we needed also a TSI SMPS with a long DMA. And then for really big particles, we had the wideband integrated bioaerosol sensor from Droplet Measurement Technologies, which goes from about 500 to 20,000 nanometers. So basically with these instruments, we were able to get continuous particle number size distributions from 1.18 nanometers all the way out to about 20 microns, which was quite helpful for evaluating the dynamics of particles emitted from different sources. So we published a paper on the nanocluster aerosol emissions, their dynamics, and subsequent inhalation exposures last year in PNAS Nexus, which is the new open access journal of PNAS. And in this paper, we provide a very nice kind of characterization of how these particles are released to the atmosphere and the transformations they undergo during a realistic cooking process. And then we wanted to evaluate exposures, specifically deposition in the respiratory system, dose rates of particles for both children and adults, normalized by body mass, because some of the articles I showed early on were looking at childhood asthma, and that has kind of initiated some of the discussion about gas stove bans. So in looking at how do we interpret our data, we like to do work with material balance models for measuring size distributions and concentrations of particles inside the tiny house. Those measurements and those results are very context specific. So those concentrations will depend on ventilation conditions, surface area available for deposition, mixing conditions, interzonal airflows if you have a real large scale home. So we want to provide some generalizable outputs from these measurements such that they can be used in modeling aerosol exposures in other environments. So we like to pair our measurements with material balance models. They do require that the environment is well mixed, which is what we do with the tiny house. We use mixing fans so we can treat it as a single zone reactor. Once we do that, we can use the aerosol general dynamic equation and predict or estimate emission rates of nanocluster aerosol from the gas stove combustion process. And that's going to be linked to various processes that affect the aerosol size distribution. So the first one you see there after DNDT is ventilation loss. So in buildings, this can be quite variable depending on the ventilation system or condition. Is it mechanical, natural? What is the ventilation rate? Do you have a kitchen hood that's activated? Deposition can be significant because of all the surface area available for these particles to diffuse to. So there's significant deposition losses to consider. And then perhaps more important are the coagulation condensation dynamics. So this is something where we want to understand the interaction between these very small particles from the gas flame and their interaction with very big particles that could be produced through the cooking process on top of that gas stove. So there can be a significant coagulation sink present because the concentrations are going to be very high of these very small nanoparticles. There's another term here to consider called coagulation source. Basically two, let's say 1.5 nanometer particles that collide, stick together, they self-coagulate. That can affect the dynamics of these very small particles. And then lastly, we have condensation, which in this case is associated with the condensation of low volatility vapor from the cooking process. So if you start cooking with butter and other fats and cook vegetables and meat and so forth, you produce a large array of low volatility compounds, SVOCs, LVOCs, ELVOCs, which we'll want to partition and condense onto these small nanoparticles. So we have to calculate condensation dynamics as well. So in looking at the dynamics here, we can start with the emissions. So the gas stove flame itself is a pretty efficient source of these small nanocluster aerosol. So we looked at both the number concentrations, their size distributions, and emission rates. Here is a plot of the size distributions, number-based size distributions down to 1.18 nanometers. This is after we corrected for the presence of the charger ions that come from the neutralizer. And once we did that, we saw a very nice elevation of these nanocluster aerosol particles down to 1.18 nanometers with number concentrations on the order of 10 to the 7 particles per cubic centimeter. So this is very high. And these are generally a few orders of magnitude higher than what has been reported based on measurements near roadways, so looking at traffic-associated nanocluster aerosol. So that's certainly important outdoors. Indoors, we see that gas stoves are a very important source and very efficient at generating these smallest nanocluster aerosol particles from 1.18 to 1.25 nanometers. So I would say we have done some measurements in years past with the particle size magnifier directly without the DMA, and it just gets saturated because the concentrations are so high. So having the DMA there worked really well for giving us this nice size resolved information that we could integrate for our mathematical model and also prevented saturation of the PSM-CPC system. In looking at the overall size distributions, merging the data from the PSMPS from GRIM with the SMPS from TSI and the WIBS from Droplet Measurement Technologies, we can have here the full distributions. And we can see that there is, a very significant presence of these very small nanoparticles, and their presence is strongly affected by how large the coagulation sink is, depending on what you're cooking on top of the gas stove. So the cooking process itself can end up generating very, very large particles in the Atkin and accumulation mode that can scavenge these small nanocluster aerosol particles from the gas stove flame. So there's two different curves here, and the blue one is for larger coagulation sinks that are associated with certain types of cooking processes. So those big particles act to scavenge the smaller ones from the flame. When we have smaller or more moderate coagulation sinks, then these nanocluster aerosol particles can exist in the air at higher concentrations for longer periods of time. But you can see here, depending on the lower cutoff of your SMPS or your CPC, you could be missing a lot of particles. So as I mentioned earlier, a lot of field measurements in indoor environments have used field portable CPCs or the P-TRAC from TSI that cuts off at about 20 nanometers. So you could be missing, a large proportion of your total number concentration if you're using a CPC cutting off at 10, 20 nanometers. So I think that's important to consider because, measurements of size distributions in field environments indoors for long durations are not so prevalent in the literature. And looking at kind of associations between nanocluster aerosol number concentrations and other indoor air pollutant metrics like NOx, NO plus NO2, and PM2.5 mass concentrations, what we found is that there's really no clear correlation. I think that's important because a lot of people may just focus on measuring PM2.5 indoors with a low-cost optical-based sensor. When somebody's using a gas stove, maybe the particle mass concentrations are not very high, and you can say, hey, the air is not that polluted, but actually it may be if you're actually measuring the smaller particles which dominate the number-based size distributions. So there's really no clear correlation between NCA and PM2.5 mass, and neither with NOx. So basically these particles have their own dynamics. They're much different than the accumulation mode particles that contribute to the PM2.5 mass. They behave differently than the NOx that is produced from the combustion process. So basically they need to be measured directly if we want to evaluate exposures. Looking at transformations, so there's a variety of things that can happen. Two small particles can self-coagulate. It's a coagulation source in our mass balance model. We can have coagulation scavenging by large particles produced from the combustion process, evaluated either if a coagulation sink or the aerosol Fuchs surface area. This is a very nice metric because you can calculate it directly from the size distributions that you measure. You don't need to run your coagulation kernel, and it's much more efficient to calculate and something that is rather straightforward to do. And we found that it's a very good proxy for the coagulation scavenging potential. The indoor atmosphere correlates very well with the coagulation sink. We have also condensational growth, again, the interaction between the nanocluster aerosol and low volatility vapors produced from the cooking process. In this case, we did some butter-based cooking, ventilation, and surface deposition. And what we found is by looking at all the different terms in the material balance model, we can understand their kind of contribution to source and loss processes for these nanocluster aerosol particles. And that's illustrated on this plot here, source on the top and loss on the bottom. And basically what you see is that there's many different colors there to different extents and magnitude, but basically coagulation source and loss, condensation source and loss, both really drive the dynamics of these small particles. Ventilation and deposition had a much smaller role. And the source and loss really depends on your particular size bin. So you have an incoming flux of these particles and an outgoing flux due to both coagulation and condensation processes. And I think what we had noted in our paper is that for some of the indoor studies looking at gas stoves and cooking, they neglected the condensational growth aspect, which we found to be quite important. Looking at relationships between an effective emission rate and these coagulation scavenging terms, the Fuchs surface area and the coagulation sink, we find that as you start cooking, as you start heating up butter or oil, you create a very large coagulation sink in the indoor atmosphere that then basically acts to remove these nanocluster aerosol particles. They're still present, of course, they're just attached to these bigger particles. So at very high coagulation sinks, shown here at the pink or Fuchs surface area, the effective emission rate, these nanocluster aerosol particles drops off. They cannot persist and last for a long period of time because they're scavenged so efficiently within the kitchen space of this test house. So that's something certainly to consider. And looking at the condensation dynamics, what we did is look at the growth rate, and we broke that down by 3 components. There's a growth rate due to scavenging these nanocluster aerosol particles by larger particles. There's a growth rate due to self-coagulation. And the growth rate we're most interested in the material balance model is that due to condensation of the low volatility vapors produced by the cooking process. So there's a nice paper published by one of the Helsinki groups looking at these different growth rates and how to account for them. It's not a perfect process, and you can calculate them or estimate them, let's say, from the size distribution measurements. But we were able to back calculate the condensational component, which is shown here in the salmon color. And it was quite significant. So the particle growth rates due to condensation with this cooking process were much higher than what we saw outdoors due to atmospheric new particle formation events. In looking at respiratory exposures, so this is where having the high size resolved information from the PSNPS worked very nicely because we can link it with our deposition fraction curves and predict dose rates for different regions of the respiratory system. And one takeaway is that the dose rates are quite significant on a number basis for these nanocluster aerosol particles, and that they're more for children than for adults once you normalize by body mass. And I think going back to the early papers and news articles about childhood asthma and gas stove use in the United States is something we have to be mindful of. And certainly children can be exposed to very high concentrations of these particles if they're present in the kitchen. And due to their lower body weight compared to adults, receive a comparatively greater body burden of nanocluster aerosol. We compared the dose rates, so number of particles deposited in the respiratory system per unit time with what you would experience if you're standing near a road based on traffic nanocluster aerosol measurements in Helsinki, Finland. And we can see there is, 1 to 2 orders of magnitude greater dose rate for gas stove use. And again, this is something I think that may be part of the puzzle with respect to the adverse health outcomes of these nanocluster aerosol and also their growth to larger sizes, certainly playing a role in some of the adverse health outcomes. And we can also look at the dose, the total dose over a 20-minute cooking period. And we calculated 10 billion to 1 trillion nanocluster aerosol can deposit in the respiratory system. Of course, that's based on the measurements in this test house, but still quite significant, and I think something that we need to be thinking about. A lot of that's in the head airways, but still quite significant dose in the tracheobronchial region. Very little dose rate for the pulmonary region, but that will be important once these nanocluster aerosol particles grow to larger sizes due to both coagulation and condensation. Once they get up to 10, 20 nanometers, then they will deposit very efficiently in the pulmonary region. So in summary, in looking at measurements, I think that the PSMPS from Grimm, and I encourage you to check this product out. It worked very well for us using the Aeromotus PSM with the Grimm neutralizer, DMA, and CPC. We had to do some of our own work with the data inversion, but generally, I think a robust product that works very well for these very high concentration events where the size distributions are changing quite quickly. Very high concentrations we measured, and by integrating this with a material balance model, which I think for indoor air quality is a very helpful tool, if your environment is fairly well mixed and you have some assessment of ventilation conditions, really helps us understand the behavior of these particles. And with things like emission rates, we can input that into an indoor air quality model for somebody's home and see what the concentrations may be. So I think that's quite helpful to consider. Very high exposures and dose rates. What are the health effects of ultrafine particles and specifically nanocluster aerosol produced from gas stoves? I don't know, but I think that's something to answer in the future. So that's all I have, and happy to answer any questions.
Leave all our questions to the panel discussion.
Okay,
Sure.
that's fine. Thank you.
Sure, thank you. Thank you for the presentation. So next will be Dr. Nusrat Jiang's presentation. So Dr. Jiang is an assistant professor from Purdue University, and her research is mainly about architectural engineering, environmental sensing, especially the detection and mitigation of indoor air pollutants. So today her presentation title is Measuring and Modeling Volatile Chemical Emissions and Human Exposures in Buildings. Welcome.
Good afternoon, everyone. Thank you so much, CY and everyone at University of Miami for creating this opportunity to come speak with you and share the research we are doing at Purdue University. My name is Nusrat Jiang. I'm an assistant professor. I have been at Purdue for almost 6 years, and it's been quite a lot of fun. I'm going to today share with you all the fun that I've had in the last few years and some papers that are highlights and have been part of this fun. So I would like to today take you from big box stores to your home. I want to take you from basically the products that you have purchased in these big box stores to what happens to them when you go inside your home. I'm going to be talking about the volatile chemical products as an important source of indoor air pollution. Many of them are widely used. They are personal care products that all of us usually use, apply multiple times a day. We also have cleaning products in all of our houses. We apply them weekly, perhaps daily, depending on the type of household you have. We have leisurely products such as candles and wax warmers that we use for aromatherapy or maybe relaxation. You will not feel very great about all of these things after the presentation. We also have paints and solvents. This is of interest to those who are always working in the house and fixing something. So basically, my presentation objective is today to introduce to you the measurement and modeling approaches for these volatile chemicals in controlled indoor environment and how do we conduct them. Thank you, Brandon, for describing our ZH Tiny House. I did want to share a little bit of a story. When I moved to Purdue, I was younger, of course, and much, much closer to the age of students. And I always felt that we were lacking a hands-on immersive experience to architectural engineering. So my first thought was to create a laboratory space where these younger generation of engineers would be able to experience all of this technology that we are so fascinated with as professors by their own hands. So basically, this tiny house is a very expensive expensive version of a normal house where it is outfitted with all sorts of sensors that a young person would be very excited to experience. My undergraduate students learn about conduction, convection, mass transport of pollutants in this house. So beyond using it for teaching, we have also made many discoveries, some of which I'll share with you today. So this was early on in 2020. We received the house after designing it for 1 year, and our first instrument inside it was Ionicon PTR TOF MS. In the picture, there is Xiaozhu Ding and Jingling Jiang, 2 of my PhD students who graduated last year, did a lot of exciting work with them. And it was a big event to set it all up. Before we set it up, it was really just an empty building. So it has been an exciting journey. When we conduct our measurement campaigns, the house looks such as this. In this case, we have set up the house to measure VOCs, HONO, ozone, NONO2, CO2, SO2. We are also working with Indiana University Professor Phil Stevens, who is working on the OH reactivity part. On the right-hand side, you see photoionization detector, which is a low-cost VOC sensor, and we have parasitic acid sensor that I'll mention briefly, and PTR TOF MS on the right side. The house is also outfitted with an energy management platform, so every circuit of it has a current transducer attached to it. So we are essentially measuring and tracking absolutely everything that can happen in this house. Of course, relative humidity, temperature, there is a pyronometer on the top. We are measuring outside parameters and inside parameters as well. So the instrument that my lab has is PTR TOF MS. I think there are so many chemists in this room. They're very familiar with this technology. It stands for Proton Transfer Reaction Time-of-Flight Mass Spectrometer. The name of it is exactly what it does, and it has been a very, very helpful tool in trying to identify and measure the quantification of these volatile organic compounds that you may be exposed to in a closed environment. So in addition to having a controlled building where you are able to actually track all of these elements, you have instruments that are measuring these pollutants. We also apply a very sophisticated mass balance model. Brandon very nicely explained it earlier. In this particular case, we are treating the house as a completely mixed flow reactor where you are able to track all the sources and the losses. So the sources of pollutants and the losses through the building ventilation system, infiltration, or whatever may be happening. I will also be mentioning emission factors and inhalation intake fractions. Emission factors are calculated as the mass of VOC that was emitted into this enclosed environment divided by the amount of product applied. The product is going to be the things that you saw on the first slide. Will go one at a time. And intake fractions are something that you are basically inhaling as an occupant. So remember, when we are using these products, we are inside buildings. So we spend 90% of the time indoors. So we are inadvertently or advertently exposed to these pollutants that they may be. So it is mass of VOC inhaled by an occupant divided by the mass of VOC emitted to the environment from whatever the source may be. So one of our first studies was to characterize what may be happening when you are conducting hair care activities. This paper was published last year, and it is focused on a compound called siloxanes. So siloxanes are very unique, big compounds. They are cyclic and linear. On the right-hand side, you see they are mentioned by their mass to charge ratio, M to Z, D3, D4, D5, D6, and L3 and L5. Those are the linear siloxanes. So we were interested in this because I have these hair that I've always been managing, and I have applied all kinds of products to these hair. And I have always wondered what is happening when I'm conducting this activity around my head. So you can imagine hair care activity is something that everybody conducts every day. Is that correct? So you have to take care of your hair. You are going to apply products to your hair. The uniqueness of this activity is that you're conducting it right next to your breathing zone. Remember, your mouth is right here, your nose is right here. Now imagine purchasing a chemical mixture from one of the stores that you go to, applying it on your head, and then using heated appliances to further enhance your hair. For example, taking portion of your hair, taking a straightener and straightening it, and this straightener is heated at maybe 200 degrees Celsius. What are we doing at that time? We are essentially volatilizing that chemical mixture right next to our breathing zone. So we are breathing the air right next to where we have volatilized it, which means essentially we are also inhaling all of the compounds that are present in this mixture. So siloxanes have been controlled in European Union now in the wastewater because they have impacted the aquatic life. In the United States, we do not have any regulation for siloxanes, and hopefully work such as this can encourage that. It is a toxic bioaccumulative compound, and we should be very interested in learning about how these compounds are just simply ending up into our everyday routine elements. So what you see here in the concentration is a 20-minute experiment where the person has divided their hair in 4 parts. They have added whatever the mixture is into their hair, and then they are using a flat iron. You will see this nice camel humps. You can see the concentration is in milligram per cubic meter. It increases with every section of the hair. You can see the very high dose that you may be receiving over time. So very interesting. We continued to dive very deeply into this topic. And if this is of interest to you, please definitely look into the paper. We looked into basically all the styling techniques. That is it, if you're using a different type of technique, will you have different type of emissions? Yes. What happens when you use different type of temperature? For example, people have hair curlers, you have blow dryers, you have all kinds of appliances. What happens then? What happens if you have short hair? What happens if you have long hair? What happens if you are a male or if you are a female? Of course, the emissions, they really vary a lot depending on, of course, the product composition as well, what type of product you are applying. So it is a complex situation, yet the results are very clearly demonstrating that any activity that will involve application of a chemical mixture onto your hair and application of heat onto that is going to exacerbate, and you are likely going to be exposed. So it is a good idea to perhaps avoid using hair care products, which is my hair look like this. So one of the other studies that we conducted was during COVID-19. When the pandemic was ongoing, the labs were shut down, and every space that I entered in, I was quite overwhelmed with the sense of disinfectants that you experienced. It felt like as if every room is a hospital room, and there is a distinct smells that we associate with hospital. So here we wanted to really test. I was thinking that, okay, not everyone is equipped with a fancy mass spectrometer. How can we provide guidance to the general industry or to the people who are involved in these disinfection activities to protect their health in terms of what kind of emissions they may be exposed to? So we decided to test disinfectant by disinfectant. We simply went to the supermarket and purchased disinfectants that are being sold on the shelf. And this is an example of an alcohol-based disinfectant. You see 3 different experiments here. We use a photoionization detector, which is a PID. PID typically gives you a total TVOC, total volatile organic compound count. It does not speciate the chemical at all, so you don't know what is the composition of it because it's always a mixture that you are spraying in the air. On the other hand, we compare it to the PTR-TOF-MS response, where we have the speciation of each of these by chemical formula. So in the little pie chart, you are able to see the difference, and here you can see the blue color is the ethanol. You can see that there's a nice trend. So basically, PID responded quite well in terms of when you are using alcohol-based disinfectant. You can see started the experiment 10 minutes. We sprayed it during the source period. And you can see that it takes about almost 80 minutes for it to decay. That means when I polluted the air inside the tiny house disinfecting, it took 80 minutes to decay. These experiments were carried out at air exchange rate of 3, which is quite high. In your typical house, you have an air exchange rate of 1. That means maybe the air is being changed every hours, 1 time. So it is really a high air exchange rate, and the decay time is quite slow. That means residence time is high of the disinfectant. That means you are inhaling also after the activity what you may have conducted in the house. So looking into PIDs, we made really a detailed study of looking into all different types of disinfectants, which are alcohol-based, lactic acid-based, botanical disinfectants, parasitic acid and acetic acid disinfectant. And you can see that the relationship between alcohol-based is pretty nice, and there is a higher deviation in the other type of disinfectant. So overall, we can say that if you were to calibrate a PID with particular different types of chemicals in terms of classification, you may have a reasonable understanding of when it is high and low. So we are able to provide these sort of solutions to, for example, integrate them with HVAC systems so that our HVAC systems can actually respond perhaps at the time when they need to evacuate all of these pollutants from indoor environments. And then again, problem does not go away. We then pollute the outdoor environment. We always have to remember that indoor is transporting outdoors, outdoor air is coming indoors. It's a cycle. So we have to think about it that way. Okay, that was very interesting. Then I thought that, hey, it is what is happening in terms of when you are disinfecting the whole space, because most of the, if you look into EPA List N, it had all the list of different disinfectants that you can use to eradicate COVID-19 virus on surfaces. In addition to that, there was a time-weighted average information that is provided for each disinfectant. So there is an exposure limit that you are setting, right? So I wanted to really understand what is happening to the exposure of the person, because spraying something is a really episodic activity. So what we did is essentially conducted mobile measurements of breathing zones. So we had PTRMS sample line attached to a person who carefully disinfected the surfaces of the entry door. You see the little feet to the kitchen countertop. Then there's a toilet bowl and a shower. Here you're seeing that the VOC mass concentrations are on the y-axis. On the x-axis, you see the time, and it's an 80-minute experiment. You will notice that the cumulative VOC mass inhaled increases over time. And every single time there was a spray, there is a peak. So during the spray period, each little footstep had a huge peak. So you are not being exposed to one threshold. It is episodic and really depends on, remember, your distance from your mouth to your hand is only this much. You are only this far from being exposed. So it really is variable. It is hard to come up with these values that are exposure limits that are just defined on the basis of one concentration, because this is something that varies. In addition to that, you are noticing that even I have disinfected the space, the cumulative mass inhaled continues to grow for certain kind of disinfectants. For example, Thymol, it sticks around in the air much, much longer than any other. So it depends on the type of the chemical compound you're looking at and how they will, how long their residence time would be inside the built environment. So looking into another PAA, parasitic acid. So this was more difficult to manage with PTR because there are overlapping ions with acetic acid. So we decided to use this HAMDAC sensor, which is a low-cost sensor. So parasitic acid, why is it important? All the fruits, vegetables that we enjoy at a supermarket, they have been sprayed with it behind in the rooms to really preserve the fruit and food. It is really used at an industrial grade. It is also available to us to use in our own houses as well. So we wanted to know what happens there, and you will notice that the PA inhalation intakes fraction are really, really quite high, even if we, even though Yeah, so you see in the 4 different plots, different mixing ratios that are presenting to you background, source, and decay, and there are multiple experiments, and each experiment, the threshold is different depending on the PAA ratio. So most of the time, you purchase a PAA bottle, which is a concentrate, and you are advised to then dilute it to certain part. When people are disinfecting at a commercial scale, they are not really measuring exact ratios. So a little bit higher, a little bit lower can have a huge impact on, what are you really inhaling and what you may be exposed to. Similarly here, so the reason we need to do this mathematical modeling of the entire mass balance equation and taking an account of all these emissions is because we want to be able to use this information and translate it to other environments, because Tiny House Lab is its own environment. And to be able to translate that, we are able to do so, for example, in this case, you notice that our modeled results show that exposure limits set by OSHA for PAA in a classroom is in the gray bar, and it has exceeded for disinfectant F, E, and D. D is hovering on it. Similarly, in case of a toilet or a bathroom, that is a more personal space because it's more closed, you will notice that the exposure limit has also exceeded. So this time-weighted average idea to create exposure limit is maybe we need to look beyond that. That may not be a very good representation of what we are being exposed to, what we are inhaling. So coming to now another source, that is wax warmer. Has someone heard of a wax warmer in the room? So wax warmers these days are being sold as a non-toxic alternative to candles. So basically, they don't have combustion properties. You just have a light bulb. You have very highly scented wax cube, which is on the top. So it would melt and it would create an aromatic environment for you to relax. Many people like to use candles to create ambience and so on. So these wax warmers are really a thing. If you go to Walmart, there's a whole like 2 or 3 aisles dedicated to it. This is just one picture. So people are quite serious about them. If you go into aromatherapy products, they are really, really big about it as well. So here I just wanted to show what a scented wax warmer product can do. They typically contain scents, and these scents have monoterpenes and monoterpenoids. They are notorious, as you know, that they can react with ozone and they can lead to SOA formation. This is why we need to care about them, which is why we wrote a whole paper detailing of what can happen when you have a wax warmer simply releasing this aroma in your environment. We basically noted that the terpene inhalation intake fractions during the source period and decay period remain very high. Similarly, the emission factors also remain very high. So we have to be careful about bringing these products into our environment. So essentially with this presentation, we have learned that the use of hair care products result in a significant increase in gas phase siloxane concentrations. This paper was focused on siloxanes. Our observations included many other chemical compounds that volatilized with application of heat. Chemical disinfectants also emit a variety of volatile organic compounds that you are exposed to even after the activity has been concluded. We also learned that these scented wax products, they emit more terpenes actually than candles because simply there is no combustion involved and there is no particular regulation that regulates how much scented product go into it. And we learned how we can use sophisticated technology together with a highly controlled environment to develop and create these, emission factors that are more generalizable and can be applied to different type of environments. I hope you enjoyed this presentation. In addition to that, I hope that you avoid using all of these products. Thank you.
Okay, great. So we are going to take a very short break and we'll come back for the remaining presentation and the panel. Right now it's 2:54, so we'll be back at 3 o'clock sharp. Okay, thank you. Trying to look at what the fragmentation patterns are. But I think UMass, so high resolution, has so many peaks.
This is better.
It really does.
Are we good? Yeah. Good. Good.
I know that is nothing, something that is on the plate. No, I can find out. I wouldn't get involved in that, but if you, let me think about it. Yeah, send me an email. Yeah. So I'll remember. Can I have your email? Sorry about that. You wanna send me an email right now? That would be. Yeah. ARS. Put down A. Dot. SH. A. R. Change the A. F. I will be next week you're interested in, and then I'll have to like people going change like seven. Okay. Tuesday. She sent me. This coming? Yeah. We have to be late. Not a weekend. No. I know, Tom.
Hey, Shana, are you here?
Yes, can you hear me?
Oh, yes, yes.
Okay, perfect. Also, I don't know if you can switch it, but I did upload a PowerPoint version. And if you want to run it through PowerPoint instead, whatever works best.
Video is off.
Video, okay. So the file is the updated one, right?
The PowerPoint is updated. Yeah. It had like 2 small things. It's no biggie, but
Here. Folder, right? Yeah.
yeah.
Okay. Well, actually, do we show it from here or actually Shana?
Oh, yeah, yeah.
So Shana, you actually share your file?
Yep. Let me get it up.
Yeah, now you should be able to share your screen.
Okay. Okay. Let's see. Where is that button? Ah, here we go. Window. Are you seeing it?
Yes. So if
Okay.
you go to presentation mode.
I have 2 screens, so it's always a challenge.
Yeah, if you present and then we can also adjust swap the screen and then.
Let's see. I'm trying to figure out where I go to click presentation mode because I'm in presentation mode in PowerPoint, but it's not. I don't think it's showing you.
The bottom right corner, there's you see the minus sign is on the left of the minus sign.
All right, hold on one second. Let's do this. No, I know. I'm in presentation mode. It's because I have a second screen. You're seeing the second screen, so I'm trying to figure out the best way to do that.
Yeah.
Hold on.
Or we can present from here. Intel has
Maybe you present from there, and I'll just tell you when to flip to the next slide. It might be easier.
come over just here.
Hi, Dr. Shumate. This is Shruti here.
Hi.
I think when you're sharing your Zoom, look into the screen too, and you should be able to share the presenter mode.
Just do it into, if I share this screen, okay, and go here. What are you saying?
Yep, you're good.
You're good.
Okay.
Yeah.
All right. I can't see comments, just so you know, but that's okay.
Okay, everyone, welcome back. Now we're going to continue our next presentation. And this one is by Dr. Shana Redenstar-Shumate. And she is the director of the US EPA Consequence Management Advisory Division. And Shana has been working on bioaerosol for many decades. She's really the expert. So we are very happy to have Shana presenting the next presentation titled The Persistence of SARS-CoV-2 on the Aerobiological Pathway. So we are getting to the biological side. Let's welcome the presentation.
Okay, thank you, everyone. First of all, Nusrat and Brendan, I'd like to thank you for scaring me about everything in my house. Every single thing you presented on today is something that I do, so I think I need to rethink some of my home life choices. But we're pivoting now to infectious aerosols and the study of them, which has been a very, as everyone knows, significant thrust in the research world in the last few years due to the COVID-19 pandemic. As CY mentioned, I'm currently with the Office of Emergency Management in EPA, which is primarily the group that responds to releases of chemical and biological materials into the environment, specifically focusing on those that are weaponized. But prior to being at EPA, as CY mentioned, I spent about 20 years of my career focusing on biological aerosols, infectious aerosols, mostly from a threat perspective. But during COVID-19, DHS, along with many other government agencies, pivoted very quickly to utilize their resources to be able to help the broader community understand how the virus was being transmitted. And so the work I'm going to present here today is work that I did while at Homeland Security, because it was such a very large research campaign that we did very early on. So did that change slides? It did not. Let's do this. Okay, next slide. Nope, nothing wants to happen. There we go. Okay, sorry. I had to figure out which button to press over here. So we're talking about the field of aerobiology, which I think for many probably has changed in definition and in usage throughout the years. I used to think it was mostly focused on the study of pollens and sort of outdoor biological materials. But in the biosecurity and public health community, it really is used to define the field of research, which is understanding the transport of biological materials in the air. And that's everything from their sources to the sinks and everything in between, and how they affect different life forms, from plants and animals to humans. And we've come a very long way from the superstitious sort of miasma theory that diseases were caused by bad air, which I always think is funny that we try to label that as sort of an incorrect thing. It's not necessarily that they're bad air, but it is bad things in the air, so to speak. And this particular field has a very significant role in public health. Everything from where do things come from, what are the sources, understanding those from an infection and transmission standpoint, through the different types of mitigations that can be implemented to minimize the degree of infection or the transmission of different diseases. So personal protective equipment, how is it effective? Is it effective? What types are needed? What is effective types of isolation, quarantining? What is true social distancing? How do things like indoor heating and ventilation and air conditioning affect the transmission of diseases? Things like vaccines and therapeutics that are developed to be delivered through the respiratory route. Survival in the environment, and a huge portion of aerobiology is, of course, the use of animal models to understand infectious diseases. And as I said, we've seen, from early pandemics through COVID-19, sort of waves in this particular field and its importance in the scientific community. And it's been very interesting to kind of feel for a good portion of my career, like I was working in sort of a box and with very little sort of public understanding of what we were doing, to suddenly being one of the fields that was sort of thrust into the open and in the media in the last few years. So we aerobiologists, aerosol scientists who study infectious diseases or bioaerosols, sort of break this field of study into three main components. The sources, so what we call the source term, which is everything from how is it released, how much is released, and what are the physical and biological and chemical properties of those releases into the environment. This can be anything like pollen released from a plant, coughs, sneezes, breathing, singing, talking, all of the things that we do or that are constantly emitting biological material, as well as intentional releases. We know that, for example, Bacillus thuringiensis is very frequently sprayed for agricultural pesticide control, as well as the intentional release of biological materials, such as the historic biological weapons programs throughout multiple countries. Once something is released into the environment, we need to understand how it's transported. And again, that really has a lot to do with its physical properties and the weather conditions and where it's released, and how that's going to influence the movement of that particle as it moves through the environment. Is it going to settle out? Is it going to be picked up by wind and currents? Could it be picked up by an animal and moved along and then re-aerosolized? Can it be re-aerosolized off the ground? All of those things are sort of contributing to the transport and the movement of that particle, as well as what's happening to it biologically and chemically as it's being transported. And that's the piece I'm going to talk about today. What's happening biologically for SARS-CoV-2 when it's finally released into the environment as it's moving along. And the final piece on the aerobiological pathway is the health effects. So we sort of call that the sink, the human who's going to breathe the particle in, the animal who's going to breathe it in or get exposed, the agricultural farm where it's going to land or be deposited. And there are various parameters that are studied there. What is the deposition rate? The deposition size ultimately affects how infectious the material is. We know, for example, that most infectious diseases, the smaller the particle size delivered lower into the respiratory tract, the less amount it takes to actually cause infection. Although that varies depending on receptors, for example, for different viruses or other sort of modes of disease. That sort of then influences the clinical manifestations, the disease progression, which ultimately influences and kind of goes circular back to the sources, because that is how you will and understand how different clinical manifestations ultimately result in shedding of material or infectious material to subsequently infect other individuals. And again, typically, studies are not performed on human subjects. So sort of the historical way that these are studied is really using animal models that recapitulate the diseases that we're trying to understand. Go forward. There we go. Oops, in the wrong direction. Okay. So during the COVID-19 pandemic, early on, as we all know, there were no medical countermeasures available, and there was a very large debate about what was the mode of infection and transmission of the virus. There was a lot of disagreement for, I don't understand why, still to this day, between the clinical, scientific, and policymaking communities of exactly what we needed to be telling people was the best way to protect themselves, and what was the best messaging that we needed to ensure that we maintain critical infrastructure in this country while we navigated this pandemic. We were also limited in the availability of PPE at the time, and so this sort of scientific debate did not help us, especially in the government, trying to inform the general public about what they needed to do to protect themselves, especially because there was differences across the agencies on the messaging. DHS itself has a mission for maintaining ports of entry, specifically TSA, airports, and other types of national security mission sets, and we needed to know how best to inform them to protect federal staff, and so that we could maintain these positions open and available. And so our particular lab at the National Biodefense Analysis and Countermeasures Center, where I was working at the time in Homeland Security, was asked to provide data to inform whether this particular virus was possibly transmittable through the air. Now, we know SARS-CoV-1 was transmitted through the air, and there's evidence that other coronaviruses at the time were transmittable. So it wasn't a significant leap to assume that SARS-CoV-2 was as well, but there really weren't enough data to say the virus is stable in the air or there's enough being emitted. We had the ability in the laboratory to at least study the stability of the virus in the air, while other university labs, including CY's group at the University of Florida, were looking at actually measuring the presence of virus in air samples in clinical environments. So our question was, can it spread through the air and how far? So how do we study that? I know I'm limited on time, so I'm going to go through this rather quickly, but we use something called a Goldberg rotating drum. This is what I would say the historical gold standard for measuring the biological decay rate of infectious material in a containment laboratory. And it's very basic. Essentially, the rotation of the drum maintains biological particles aloft for periods of time that allow you to measure a reasonable amount of the infectious material over a period of time that is representative of what happens in a normal environment, not in a static laboratory chamber. So the idea is you can take samples over hours or minutes to hours to even days, depending on the design of your drum, and collect samples over time and look at how much infectious material is present. In this case, we did this with SARS-CoV-2 in a simulated respiratory fluid. It was simulated saliva. There's much to be done in the work of what the best matrix is for aerosolizing these viruses for studies. And the uniqueness of our drum is that we have the ability to modulate temperature, relative humidity, and simulated sunlight in real time in the drum so that we can measure those biological decay rates as a function of those environmental conditions. It's quite a unique capability to have all three of those particular environmental parameters able to be modulated in a high containment lab in a rotating drum system like this. So our goal was basically we fill the drum with infectious SARS-CoV-2, we change the temperature, relative humidity, and stimulated sunlight to the conditions that we want to measure, and then we take periodic samples throughout a different duration of time, depending on the conditions we're testing, and we look to see how much infectious virus is still present. This is an example of what the data look like. This is an example at 10 degrees C in complete darkness and at 70% relative humidity. And what you're seeing here on the left is the viral aerosol concentration. So this is log 10 TCID50, which is median tissue infectious dose. And on the right, you're seeing the aerosol mass concentration measured with an APS 3321, which is just the mass concentration of the aerosol over a period of 0 to 60 minutes. And the slope of this line actually represents the decay constant in a monophasic decay system. So essentially, we're measuring the decay rates between the aerosol mass and the total loss of virus particles. Now, the total loss of virus particles includes the physical loss of the particles due to deposition on the rotating drum surface or the sampling process. So what we can do is normalize for that by subtracting the physical loss, and that essentially gives us what is known as the biological decay rate or decay constant, which can then be used to predict for any longer period of time what the actual decay rate is for that organism and can be subsequently used to model. This is an instance where both the physical decay as well as the total decay are very similar. When we look at a condition where the virus is not as happy, we see, for example, at 30 degrees C and 1.9 watts per meter squared. By the way, I didn't mention this, but this is the integrated UVB intensity. So basically mirroring the UVB intensity for a very sunny day. This is representative of the summer solstice in the continental United States at 40 degrees north latitude and a lower R range. You can see here how quickly the two slopes differ from each other. So this is an example where the virus is being activated much more rapidly because the physical decay is not tracking as with the viral decay itself. Okay. So as I mentioned, this took almost 7 months to complete because, as we all know, it takes a really long time to grow virus, and you're doing this in a high containment laboratory, and it takes about 7 days to actually get your results back for every experiment. Sometimes you do an experiment and you completely mess. We did over, I would say, 150 total experiments across different parameters, virus culture media, whether we did saliva, respiratory tract fluid. These data are only representative of the saliva, but we study this in many different ways across many different environmental conditions. And the big take home that I want to show you here is really, because we're here today to talk about indoor aerosols, is what happens in the zero simulated sunlight. So this is darkness indoors. And what you can see is that, generally speaking, the biological decay constant is very low, about less than 2% per minute. For most of the different temperatures and relative humidities that we measured. We do see at a higher temperature, around 30 degrees C, that the biological decay constant or decay rate actually increases to about 6.3, or even at a higher temperature at 20% relative humidity, it's at 3.9, but it's still relatively low compared to when we look at data, for example, at a mid-intensity simulated sunlight, so outdoors, or even in full intensity sunlight. You can really see what is driving an activation of the virus. This was information that we could use very quickly to say your risk of transmission is outdoors. So spend more time outdoors when you're hanging out with people instead of spending time indoors, and sort of what potential ways people could be sort of avoiding being in large crowds or waiting outside or host things outside if possible whenever. These were sort of the early types of data that we were using to sort of provide information about the risk of getting exposed.
Hey, Shana, we have to quickly wrap up this 1 more minute.
I am almost done. This is a summary of all of the decay constants across all of the environmental conditions that we studied. And what I will say is that we were able to do a linear regression and develop predictive equations where you can put in temperature, relative humidity, and solar intensity and be able to get a biological decay constant that is predictive. I won't go over this for a second because this is sort of the implications of that. But what I will say, since we're running out of time, is that these data were then ultimately developed into a predictive model that can be used to, again, based on the UV index, temperature, and relative humidity, get a biological decay constant. And why is that ultimately important for this group? If you're doing different types of mitigation technology development for whether it's UV, ozone, or other types of methods that are being developed for cleaning indoor air in order to reduce infection, you first need to understand how long the virus is going to remain active in an indoor environment. And sort of these data can help basically drive those models for doing those predictions early on. And I'll stop there because I know I'm out of time. And by the way, thank you, ChatGPT. I asked it to make a picture of SARS-CoV-2 on the aerobiological pathway, and this is what it came up with, which was quite fun. So.
Thank you, Shannon. So there will be questions and we'll leave it for the final panel discussion. So our next speaker will be Dr. John Douglas, who is the Director of Healthy Building Services and Solutions at Johnson Controls. He mainly work on how they can enhancing the design and performance of HVAC systems. Okay, Dr. Douglas is especially especially interested in leveraging new technologies such as big data and IoT, Internet of Things, to improve the performance of the equipment. So today, the title of his talk will be Energy Efficient Strategies to Reduce the Concentration of Infectious Aerosols.
All right, can you guys hear me?
Yes.
Awesome, okay. So, well, thank you for the opportunity to present here today. I think this is really fitting how the timing of the presentations went together. I'll give you a little bit of background about myself. I work actually in the sales organization now, and my job is to basically go to the seminars like this, learn all about healthy buildings and indoor air quality, and then translate that into material that can be used by our salespeople to advocate to our customers about how to deploy healthy building solutions in their buildings. So what I'm going to do is start out with our simple summary of indoor air and then go into an example we did with MIT. So let's go to this first slide. So when you think about indoor air pollutants, there are three main categories. And what's really cool is each of the three was covered in the three previous presentations, right? So if you look at particles, right? Brendan kind of talked about all the particles that are generated via cooking. We've got smoke from fires, cooking. You can stir up particles with cleaning. You've got the gas phase pollutants, and Nursat talked about a lot of that in the chemicals that we use in our normal healthcare products. And then finally, you have pathogens, and we just heard a nice presentation about those. So then the question is for our customers is, okay, given that we want to get rid of those gases, particles, and pathogens, what are the mitigation measures we can do to do that? And so the first one we have, and this is very commonly used in ASHRAE 62.1, is outside air ventilation. And the general theory is that outside air is cleaner than inside air, and it's good for diluting those gas phase pollutants that are generated inside the building. So it's good for gases. It's not so good for particles. Generally, the particle concentration outside air is higher than in its inside air, but it's also pretty good for reducing the concentration of pathogens in the air. Assuming you don't have a sick person in your outside air intake. So we've got outside air is good for gases and pathogens. Think about the other thing you can do in a building system is filtration. Filtration doesn't do anything for the gas phase pollutants. They pass right through the filter. Obviously, it's great for removing particles. And it turns out that pathogens are respiratory droplets, so the filters are actually pretty good at getting rid of pathogens. And then finally, you have disinfection methods. I highlighted UVC disinfection, and pretty much the primary use for that is in getting rid of the pathogens. So when we talk about managing infection risk in buildings, what's really cool is we actually have three distinct tools we can use. We can use the ventilation, the filtration, the disinfection. The last column here are labeled the sensors that we can use to detect the efficacy of these different mitigation measures. For outside air ventilation, we tend to use CO2 as a proxy for the amount of outside air. We can also directly measure the outside air ventilation rates. For filtration, we tend to use the PM 2.5 sensors. We can also measure the filtration effectiveness and airflow rate is another way. Unfortunately, for UV disinfection, there really aren't good field sensors that can measure the effectiveness of UVC's disinfection. So that makes that a little more challenging. So what I'm going to do is go to the next slide and talk a little bit about, one last thing is these are all the tools used in the new ASHRAE Standard 241, which is a method for controlling infectious aerosols in buildings. So now what I want to do is talk about a research project we did with Dr. Martin Bazant at MIT. The idea here was to understand and study the energy efficiency impacts of MIT's pandemic response during COVID. And so MIT, their strategy was basically, let's go to 100% outside air. wherever we can. And so what we did is we actually collected, we got a lot of nice data sets. We worked with the facilities folks at MIT and got access to all their building automation systems data. We went in and installed indoor air quality sensors in certain rooms. You can see this is a picture of the sensor. It's a Kytera sensor with a wireless communication. And then we actually had graduate students go out and count the number of people that were in the classrooms at different times. And all this data came together and it went into an analytical model for infection risk. It's basically a Wells-Riley based model that Dr. Bazan had for modeling the risk of transmission. And then we at Johnson Controls have an infrastructure of tools that can measure the and model the energy consumption of different mitigation measures. And I put the link to the paper here. So next, and this is just an example of some of the data we're getting. So here is on the vertical axis, we have CO2 concentration. We are measuring the outside air. So you can see on the bottom here, most of the rooms were running, about 5 air changes per hour of outside air. There's some rooms that have, this was an older building that didn't have a ventilation system, so it had very low outside airflow rate. And this was an office that was controlled on and off. And then you've got the CO2 levels. And you can see that this is basically a zoom in of this gray bar. You can see, for example, the space that didn't have a mechanical ventilation, the CO2 levels get much higher than others. And you'll see different levels of CO2. You can see that on the weekends where there's nobody in the buildings, CO2 levels are considerably lower than during the school days, which would be an opportunity to save energy. You can also see that this one room here, the CO2 peaked, but then went way down. So you could save energy by adjusting the ventilation rate. One of the fundamental things that we do when you use the Wells-Riley model is you're assuming a well-mixed space. And there's a lot of debate out there about whether spaces really should be well-mixed. So what we want to do with, one of the things we want to do with this study is investigate the merits of the well-mixed claim. And so in several spaces, what we did was we measured the CO2 levels just with one sensor placed generally in the middle of the room or along the wall if we couldn't get into the middle of the room. And then we had actually graduate students go in at different times in different class periods and just count how many students went into the room. So what we did then here is we just used a basic mass balance equation. I got the equation here to take the CO2 level, since we know CO2 and we know the ventilation rate from the building automation system, we can back out the occupancy. And so that's what this classroom occupancy is here on the equation. And then the dots are actually the occupancy as measured by the graduate students. And so you can see here's a classroom. And you can see for the most part, we got the occupancy of that one class pretty dead nuts on. It's about 30. We modeled 30. For the office, it's a little more challenging because the number of people are going in and out throughout the day. But you can see for the most part, the occupancy calculation based on CO2 tracks what we count, the physical people counting. So we think that this is indications that well-mixed is probably a reasonable assumption for these infection risk models in terms of pollutants generated by people. So then we went on to our modeling, and this is the results of the model. Again, we have the model from Dr. Bazan, which is the infection risk, which is this bottom axis right here, which is the transmission rate. To the right is bad, to the left is good. And then we used our models to model the energy cost per day. And then each of these blocks is a different use case scenario. And so you'll see that there's like an oval here, right? Not just a dot. And this oval here on the horizontal axis is just variation in infection risk due to, for the most part, variation in occupancy in that space throughout the monitoring period. So you'll see there's quite a wide variety. If the space is empty, you would have very low risk. If it's very crowded, you'd be on the higher end of things. And then you have the vertical variation. That's a variation in energy cost. And that's just due to if you're bringing in outside air and it's really cold, it's going to cost you more than if you're bringing in outside air and it's much more mild. So that's kind of the variation in energy costs. So that's why we have these clouds. So As I mentioned earlier, the MIT strategy was to just crank up the amount of outside air. And the result is this blue bubble here, with the center being this dark blue square box. The other context I'll give you is this dashed line here is the infection transmission risk that would be advocated if you did the ASHRAE 241 calculation. So if you're to the right of this line, your risk would be higher than what ASHRAE 241 would advise. If you're to the left of this, it would be less. So, MIT is right here. So what we did was we modeled what would you do, what would be the energy impact if you changed to different strategies. So that's what I'm going to show you next. So the first thing we did is looked at, okay, as you looked in the previous one, if we just turn the ventilation off when nobody's around, what can we do? And you can see we dramatically reduced the energy cost, right? We went from 2 to just above 1 with just a slight increase in infection risk. And that's because there are some people in those buildings when they're unoccupied, so their risk would be a little bit higher, but it's a very small increase. The second thing we looked at was then, okay, what if you, instead of going to 100% outside air, you went to just doing the outside air required for ASHRAE 62.1. So again, very, very significant reduction in energy costs, but also a material increase in infection risk, because you've now reduced the amount of pathogen removal because your outside air has been reduced. Then we looked at, okay, what if we did demand control ventilation, which would be even a further reduction in energy efficiency, I mean energy consumption, but again at a slightly higher increase in infection risk. So we're in this flow, we're saying we're trying to save energy and seeing what the consequence is in infection risk. So there's kind of a line here. So the next thing we did was we looked at other strategies, not the ventilation strategy, but other tools that we could use for managing the infection risk. The first one we looked at is just filter. So this is like the Corsi-Rosenthal box, right? So the idea is you start out with 62.1 ventilation, you add in-zone filtration, and we adjust it so we would hit exactly that 241 level. And you can see we did increase energy consumption by some, but we materially, very significantly reduced infection risk and got to the line. So filtration is really a good tool for managing infection risk in buildings. The second part of this, second choice we did was we said, okay, what if we added an in-room UVC solution? And in this example, we modeled far UV lights that are down lights in the room. And you can see here we got the same level of, we designed it for meeting 241 level of disinfection and at an even lower energy consumption. And so if you look at the idea of using ASHRAE 62.1 and a combination of far UVC, you could get a 65% energy reduction and a 20% transmission risk reduction relative to what was done at MIT during their policy. And then if I'm going to clear this out here, let me go back. I also want to mention that this pink one is sort of the idea of blending the far UV and the filtration, and if you throw it all together, you get the plus. That's quite a bit more capital cost. So the last thing I wanted to end up with, which is just sort of a little bit of a side topic, but I just wanted to talk about the importance of monitoring. This is a recent trip I was on, staying in a hotel, very new hotel. We were doing an air quality audit, so I had a ton of instrumentation with me. And over here are the CO2 levels measured in my hotel room, and then I actually added in measurements measured in a colleague's hotel room the next day. And you can see that on the first night, CO2 levels were very reasonable, 800 to 1,000 ppm. Everything was good. The next night, I thought there's maybe something wrong with my instrumentation, but the CO2 levels went almost to 2,000 ppm. And that was both in my room and my colleague's room. And we didn't notice anything. I looked at the data the next day and saw this and actually went to the facility manager, and we looked around, and it turns out that the dedicated outdoor air unit had a fault and shut down. And so they were able to reboot it and get it up and running. But the key point here is that if we had not been monitoring this, we wouldn't have known that they were the hotel was getting poor air quality, and it could have gone for weeks shut down without this monitoring. So I think that's it. Again, advocating a balanced approach for managing infection risk. Outside air ventilation, filtration, and disinfection are all useful tools. We find that filtration, upgrading your filtration is the first thing to do, and then starting to look at UVC disinfection. So that's it. Thank you.
Thank you very much. And we're going to leave the question toward the panel session later on. Next one, we are going to have our final presentation by Dr. Pravars Shukla, and he's Associate Professor in the Division of Infectious Diseases, and also he's a Medical Director for Infection Control for the entire University of Miami. So he led the efforts during the COVID pandemic for the entire university. So his presentation title, yeah. So as you can see, the title is Indoor Air Quality and Infectious Disease. Let's welcome Dr. Shukla.
Thank you so much for having me, CY. And just a full disclaimer, I am not an engineer. So I'm going to talk a little bit more about the applications of a lot of the work that's been already described here in the real world at the point of care setting. And I don't have any disclosures. I'm going to talk a little bit about the history of contagion spread, but I think one of the last speakers did a nice job of summarizing that already. I'll talk a little about what was sort of the normal state before the pandemic began for our health system. And then obviously what all the lessons that we learned, not only just from the overall perspective, but also from being on, boots on the ground, being there all the time perspective. And then the opportunities that a lot of this research, I think, has. So just as a little bit about background on the history of the understanding of transmission of infectious agents by the air, this history goes back to antiquity. There's, plenty of discussion about bad air, which was discussed previously by the Greeks and the Romans and so forth. So it's been something that's been very well suspected for a long time. By the time public health sort of reached a new era, I would say, under John Snow and the time of in the mid-1800s, there was a lot of, most of the sort of outbreak investigations that were done found that people who were in close proximity to each other were most likely to spread disease. And so again, in that setting, air was suspected, and this sort of led eventually in the 1900s to Chapin studies and the understanding of droplets being the primary mode of transmission by the fact that most transmission was occurring with people who were in close proximity to each other. Now, obviously, I think we know a lot more, and that obviously aerosols can also transmit that way. But that really wasn't, that sort of became sort of the dogma of the time. The first pathogen to really be understood and proven to be transmitted by airborne route was tuberculosis, and that was done with a number of very interesting experiments wherein someone took a exhaust from a TB patient room and exposed pigs to it, and those pigs went on to develop TB. And so that sort of became the sort of proof of concept about aerosol transmission, and that was sort of the first disease that it was described in. And then it sort of became the norm to, in order to show that a disease was transmitted by airborne route, it almost had to disprove the droplet theory. And so that's kind of how it proceeded with measles, for example, wherein a pediatric clinic was noted to have patients who developed it later on after a patient had been there for a while and so forth. So basically that dogma kind of persisted. And by the time the COVID-19 pandemic began, there was still this sort of belief that there was a droplet as a primary route of spread, especially in the early days of the pandemic when descriptions of the transmission was occurring between people in close proximity. So what was this sort of normal state right before the pandemic began? And most hospitals, first of all, hospitals and health systems are very highly regulated in the United States. There are a lot of standards that have to be followed. We joke about how many different regulatory groups we have to report to. But in terms of the management of air, most of the guidelines that we follow are ASHRAE standards. So this is just some of the standards that were in place in 2019. So the requirement for air filtration, optimizing of air movement, temperature, humidity measurements, et cetera, this still goes on now, and it did at that time as well. And in general, the idea is you want to have positive, in terms of pressure, you want to have higher, you want to have positive pressure in areas that are clean, quote unquote, and areas that are dirty, where there's dirty equipment or an ill patient, negative pressure preferred. And then there's special considerations for isolation rooms that are in those guidance documents, protective environments for patients who are highly immunocompromised, operating rooms where obviously you're trying to maintain sterility, pharmacy compounding areas, medical equipment areas in terms of cleaning areas and storage areas. So again, lots and lots of regulation around this. And just to give you some example, this is the sort of figure that they provide in the ASHRAE standard for an isolation room. And as you can see, for you guys, it's probably very simple to appreciate this, but for a facilities manager for a hospital, this can be very laborious and require a lot of staff and be very expensive. And so generally, pre-pandemic, most hospitals would have, depending on the size of the hospital, maybe a few of these type of rooms set up, right? So for the occasional tuberculosis case or the occasional varicella case, so forth. So where you need to where it was accepted that those were transmitted by airborne route. So, but again, you would need an anteroom, you would need the actual room that the patient stays in, you need an exhaust system, and a high mortar rate. So it's basically a very complex system to set up for a large number of people. And that sort of became the leading challenge when the pandemic began, because most hospitals when it began didn't really have the capacity for having large volume of patients that required airborne isolation. And this is just another figure showing you the operating room requirements. And again, it's very detailed and intense. So, you guys are all much more familiar with the science behind aerosols and droplets. So I'm not going to go into that. But what I will highlight here is that in the last 25 years, and as you can see, how much, if you just search aerosol and droplet keywords in PubMed, how much literature has come out in the last 4 years because of the pandemic. And we've learned quite a bit. Many people have already talked about this, and you guys are probably very familiar with this, much more than I am. But just there was I think, a very reawakening of this conversation about aerosol transmission and the persistence of aerosols in the air as being a mode of transmission. And I'm just highlighting here sort of a summary figure. What was our take at the UHealth system? I'll kind of go through a lot of the discussions and planning that we had actually began because we also have an annual preparedness plan that we have to put together for infections of high consequence. So this usually involves thinking about an Ebola case and how you would handle that, but kind of translates to any sort of a high consequence pathogen. And we had just gone through that process in October of 2019 and had sort of done a review of the inventory and all the things that we had available. Many of the Ebola equipment we had, for example, had expired, so we just ordered new equipment. So it kind of worked out well in the sense that we were already sort of equipment-wise prepared. And by the time January and February rolled around, we were expecting, and March rolled around, we were expecting 2020 a lot more patients to come because we were an urban center with a lot of travel. And actually, we didn't have a really big surge until the summer. So we had a lot of time to prepare, so to speak. And to the left, so anyway, in that sense, we had the luxury of time to prepare, and we had this conversation about whether we're gonna think about this as an airborne pathogen or not, and we chose to do so. And so from early on, we had created on the left side, you can see this is in our emergency room area. We kept the testing areas in the outdoor space in the outside of the emergency room, themselves equipped with exhaust and basically negative pressure for those little tents. And we did something similar for the drive-through testing site, the first testing site that we had created. And everybody was already equipped with PPE that was appropriate for aerosols, even at that time. So we were sort of well prepared from that perspective. Even for the eventually when we did start getting a surge of patients, we sort of configured the hospital as well on the inpatient side. So this is actually a very early picture on the left side of the isolation wards that we had created, and this eventually became closed doors. And so what we sort of created was an airborne isolation wing as opposed to just rooms, which was sort of the norm before then. So you would go in through a door before, like behind this picture was a door. You'd walk in, this little space would then become the anteroom, and then you would have the two further doors to get into the actual patient care areas. And in the schematic here, you can see how we sort of set it up. We had the first ward on the very top of the hospital. The engineering was able to drill some holes so that we were able to create exhaust to the outside from the top of the hospital and reconfigure the HVAC. Essentially, we were able to basically create a negative pressure for the entire hallway. And then eventually, when we were at the peak of a lot of the years of pandemic surges, where 40% of the hospital was occupied by COVID patients, we actually just used the same system and moved the HVAC system down one floor. So we were able to adjust up and down as the surges came and went. And this was like very flexible and allowed for the rest of the hospital to run for uninfected patients. The other thing that we were able to do that we had planned and we had the luxury of in the building was we had all single patient rooms and they were equipped with capabilities for ventilators. So instead of moving the patients around the hospital like you would normally do for studies or for the ICU, et cetera, we would bring that equipment to the room. So instead of the patients being circulated, the staff and the equipment would come to them and go out. So that actually allowed us to minimize a lot of transmission risk just within the staff. The staff also felt a lot safer, especially as more data emerged that this was definitely potentially aerosolized, especially doing aerosol generating procedures, which also there was a lot of debate and discussion on initially, but became very clear by this point in the pandemic. So there's a lot of sort of boots on the ground that occurred in order to maintain this airborne pathogen. And I think that's one of the biggest limitations from a public health perspective, where the WHO, for example, took a long time to accept the airborne transmission route. And I think it's because, as a public health agency, you kind of have to think about things beyond the health, but other things that people will sacrifice for their health. So if you're in a country that has very limited capability for these things, saying this is airborne and now you need to have this type of setup everywhere in the world is very difficult to do. Even in the United States, a lot of hospitals struggled with this because they just didn't have enough rooms and the patients were just coming too fast. And then there was also the PPE issue. If you tell the lay public you should be wearing a respirator, those people don't know how to properly wear them. They need to be fit well. Otherwise, they're worse than not even having a regular mask. And so there's a lot of, I think, nuances to the messaging. And, God bless the people who had to work in that setting in the national level. Luckily, I didn't. But it's tough to send out the right messaging in that setting. So most hospitals, I think in the US sort of did their own thing and did what they could based on what they had. So the other things that I'll mention that we did to sort of minimize the aerosols, we definitely did a lot of, now I realize maybe we exposed a lot of cleaning folks to disinfectants, but we definitely used a lot of disinfectants, which maybe they neutralized some of or maybe they helped decay some of the particulates in the air. And then we also use a UV system. So we have a UV system that you roll into the room and it sort of does a circular, I don't know the exact exposure from the UV, but it does a continuous exposure once the room is vacated. So we also did that. So a lot of work went into making sure that these rooms were safe. So there's a lot of lessons learned, but I think, and a lot of people have spoken about this already, but I think some of the key points that I'll mention from a health perspective, CY and other people who did work on this recognize that viable virus can exist in suspended air, which is, I think, a new concept really in healthcare at that time anyway. Host viral shedding can be highly variable, we learned, because that's another point that, the generator of the aerosols, what they're actually shedding can vary depending on their immune status, depending, now if they've been vaccinated or if they've had a prior infection and so forth. The symptoms don't necessarily correlate with the amount of shedding. So that was another big aha moment. I think traditionally we think of the patient developing symptoms and then being tested and so forth. But we learned very much in this pandemic that asymptomatic people could also be shedding viral particles. And then PPE can have an impact. There's a lot of research that went into the effect of PPE, including the respirators, N95, or mechanical, as well as for general masking. So a lot of lessons learned. And I think ultimately, and then there's a few more things I'll mention here, but ultimately what I gather from this, and I'm not an engineer, but if I had to make an equation, I would include some of the human health factors as well that we don't think about outside of the air. So obviously, there's multiple equations about the risk from air particles, but integrating the other variables, I think, from the human perspective, their immune status, whether they've been vaccinated, whether they have a long exposure, short exposure, And then also sort of the outcome factor. In other words, what is the health outcome if they do get exposed? Is it, sniffles for 5 days, or is it the ICU, right? So I think those are all sort of factors that we also should think about, because ultimately what the public and the individual really wanted to know is, what do I need to do to be safe? What is my individual risk? And I don't think we have really ever been able to answer that question. So what's going on in the discussion in the medical world? So we talked to some people from other federal agencies. So the CDC has a subgroup called the HICPAC, which is sort of the advisory panel for health systems and hospitals. And they have had basically an ongoing 3.5 year discussion on what the advice should be in terms of droplet versus airborne. So this is the latest iteration of that, which is from their meeting in November of last year before the holidays. And again, they're still in the debate phase. So early last year, the draft said they wanted to continue to recommend general masking and assumption of droplet transmission for respiratory viruses. And then once confirmed that it's an airborne, to switch then to respirators and engineering precautions. Now they're flipping that again. And this is, like I said, the latest draft. Now they're suggesting doing an N95 up front, then figuring out what's going on. And if it's a low consequence pathogen, switching to droplet. So again, it's tricky because this advice then is going to have a lot of implications. So, for us, it might mean, no big deal. I agree. That's great. But that could mean, for example, if they put this in place, then everybody in my emergency room needs to be wearing an N95 all the time, forever, basically, because there's plenty of respiratory viruses that walk into the emergency room. All of my intensive care unit providers need to have an N95 all the time, because half of those patients are generating infectious aerosols, either through intubations, extubations, or any other medical procedures. So it makes it it kind of changes the whole paradigm about what you're advising your staff to do and what's safe. So that's probably why these type of conversations have been going on and on and on for years, because whatever advice you give to people has a lot of implications for the operations of the hospital, the equipment, the training, and a whole host of other things. So moving on from viruses to other pathogens, my own background is in studying antimicrobial resistance, which has nothing to do with viruses, except for that you can use some phages to treat that. But aside from that, so what else can we explore in this space? So in the infection control world, we look at things sort of from once they happen back. So typically, we're not continuously monitoring for pathogens in the air, but when there is an outbreak of XYZ pathogen in the hospital, then we start investigating, is it the water source? Is it what their medications they were getting? Is there contaminated equipment? Is it the surfaces? Is it a person not washing their hands, going room to room? And we do a full line list to figure out where the outbreak source is. But that's a little bit late in the game already. We're not necessarily doing surveillance for that, except for on the patients, right? So we test patients for specific pathogens that are prevalent in the community as a surveillance mechanism, but not the actual environment. So I think there's a lot of opportunity to try to understand how we can survey that. So for example, we have outbreaks from bacterial pathogens, and now have been a couple of papers on outbreaks related to sinks. But is it the sink water splashing in droplets? Is the sink water aerosolizing? Those type of things are rife for study by folks like you guys, and maybe with a collab with me and people like me. But I think there's a lot more to learn in this space, and the sort of skills that you guys bring to the table can help us a lot understand how we can improve the lives of our patients as well. So in summary, I think understanding of aerosols is very, very of high consequence. And I think what COVID has started, we should certainly continue those studies. It has a lot of impact on not just obviously, universal pandemic on preparedness, but also for individuals to understand what is their risk when they're walking into an environment. And I think what I would say, having gone through this, is that these type of mitigation efforts require a lot of stakeholders. It's very difficult to manage a large population of having a specific disease at the same time suddenly. And then I think what we learn from these type of experiments can also help us manage future pathogens, and that can also help us train and educate medical professionals and the community as well, where I think the understanding of aerosols is just very poorly understood. because of their educational background. So, and that's basically a summary. Thank you to my team. This is my team for the infection control group at the tower, at the health system. And we were all very involved in the pandemic days. So very good group. I think that's it.
Now we'd like to invite all the panelists to come over here, and we're going to start our panel discussion. Oh, yes. So we'll have a Q&A, but before that, so one of the key challenges and barriers that you implement advanced indoor air quality methods is residential versus commercial buildings versus a hospital settings, and how can we overcome these barriers? Oh, yes. Got it. Yeah, so the question is, what are the key challenges and barriers to implementing advanced indoor air quality control methods in residential or commercial or say healthcare settings? And how can these barriers be overcome? Can you come over here?
Well, I think I talk a bit about the residential space. So I think one challenge is ventilation in homes. Many homes do not have proper outdoor air intake through mechanical means. So rely on infiltration of outdoor air that's uncontrolled. I would say that one thing we can do to improve indoor air quality control in homes is to implement ERVs and HRVs as our energy recovery ventilators or heat recovery ventilators. I think this is a technology that has not been widely adopted in the United States. But basically, and this kind of goes to what John Douglas was talking about, provides an energy efficient way to improve ventilation with respect to outdoor air in the residential environment. With an ERV or HRV, basically you pass in outdoor air, you can preheat it or pre-cool it by exchanging energy with the exhaust air from the indoor environment. We have a facility on campus called the Renew House, which has ERV. And I think it's a pretty wise solution because you can provide dedicated outdoor air to the building. It can be integrated with the central HVAC system. That outdoor air, if it's properly filtered, is an effective mitigation strategy. I think the problem is many homes in the United States do not have an ERV or HRV, some in the northern states, but I think this is a very good solution. Another thing I would like to add on to that is we want good indoor air quality control. I think we need to be measuring a variety of indoor air pollutants. Perhaps in public spaces, we're measuring carbon dioxide, and that's about it. In the home, perhaps you may have an indoor air quality monitor that you can purchase, but it doesn't communicate with your HVAC system. It doesn't communicate with your kitchen hood, your bathroom exhaust, or your portable air cleaner or anything like that. So I think, you know, we could outfit buildings, especially homes, with technologies like ERVs and HRVs. We can install indoor air quality sensors that measure a wide variety of pollutants that come from different sources, and then have those sensors communicate with the building systems with portable air cleaners. And there's some smart air purifiers that do this already with kitchen hood exhaust. Surprisingly, there's not many kitchen hood exhausts that will automatically activate when you start cooking. And, you know, try to both monitor and control for a variety of gas and particle phase pollutants. And, you know, try to balance, you know, improvements in health with energy cost. which is certainly an important consideration for the homeowner.
I'll take a shot at it too. So in the commercial space, a lot of decisions are made based on economics and financial metrics. And so we need to figure out a way. We all go to presentations and we see the health benefits of improving indoor air quality, whether we're talking about contaminants or health risks. But there's really not much data that maps that improvement in indoor air quality to quantifiable health improvements, right? How do we translate that into dollar improvements for the organization? When we talk with our customers, we always like to use the GAL 330-300 model, which generally the rule of thumb is that you spend about $3 a square foot per energy, $30 a square foot for the rent or the capital of that building, and then $300 a square foot for the people that are in the building. So if you think about it, if you can just improve the productivity of the people in the building by just 1%, it's equal to the whole utility bill. Yet the challenge is that there's no productivity meter in a building. There's an energy meter. And so we spend all of our time working on energy savings measures to work on that $3 a square foot and instead of spending time doing indoor air quality measures that can work on that $300 a square foot.
Any other? If not, maybe questions from the audience. Can you come over here too?
I have a question specifically for Dr. Chung. You gave many instances of like how some products that we use at home could potentially lead to higher exposure. So this question is like, okay, one thing is that you may stop using those products, but if you were to advise those manufacturers of the products so that we do not get exposed to, what would that advice be?
Can you come over here?
Thank you for your question. Yes, I think it's quite important for the product manufacturers to look into the composition of the chemical mixture they are putting out on the shelf for people to purchase. So I think somewhere we are forgetting that there are real people buying these products and using that in their homes, in their personal environment. And these products may be tested for what they immediately do and can do, but they are not tested from perspective of what they do to the air quality once they have been released into the environment. For example, most of the hair care products, siloxane as a compound is put in the mixture to stabilize because it's a very good heat resistant. So they are selling that as a heat resistant product while you are applying heat to your hair. At the same time, nobody cared to investigate that it is volatilizing and actually you are inhaling it and you're ingesting it and it is bioaccumulative. So that thought process did not go into creation of the product because of which we ended up with it in the market, right? So I think it's very important for the product manufacturers to consider the implications of the products or the chemical mixtures they are putting out on the shelf. And these implications have to be aligned with public health as a priority metrics. So my general advice to everybody would be to simply avoid products that include fragrances. I think that's the number one thing that you can do to protect yourself, reduce your own personal exposure. The second thing you can do is to really focus on ventilation control mechanisms that is present in your house. You should definitely utilize your kitchen exhaust hood. You should definitely check out your filtration media if you have a central air conditioning unit. If you don't have control over the central air conditioning unit, you can definitely purchase a personalized air cleaner or an air filter box. It is possible to really create that even by yourself. Corsi Rosenthal boxes are a good example of how you can simply, put 4 filters together with a fan to create a nice unit for yourself. So think about reducing your personal exposure whenever you are purchasing any product from the market. Always turn the product around to check what ingredient list may be. Siloxanes are of many kind, or particularly for siloxanes, just look for the word siloxane in it. It can be decamethyl, so it can be quite difficult and tedious to read. Environmental Working Group has done a good job in trying to identify products, but if you go on their page for siloxanes, it's still not updated. So, it's almost like as an American consumer, you have to be simply vigilant and sort of responsible for looking out for your own benefit. When I was in European Union, I had a little bit more faith in how the regulation metrics work there. Yeah, so that would be my 2 cents of what we can do ourselves and what can the product manufacturers do. Thank you.
So first, thank you for the wonderful presentations in the afternoon session. I feel like we covered a lot from how the indoor sources were generated to how they are ventilated. So I'm kind of very curious, like the ventilation, does it I think it must related to particle size, but do we know like which size is favored and which size is not favored? And also regarding composition, do they like more efficiently remove certain type of aerosols? So that's the first 2 questions. And my third question is, I feel like Dr. Douglas talked about like how we want to economically control the indoor air quality, but the harmful particles are very few in the air. I feel like if we don't target them specifically, we are kind of like picking out 1 or 2 particles that's toxic or infectious among a lot of particles in the air. So is there a better way that we can do it, like improve it for with the next generation technology rather than doing just the general ventilation? Can we target certain type of aerosols to do the ventilation? Yeah.
I'll start with that one. I think that we're limited by our sensing technology, and that we still, for example, we've been talking about it on 62.1. We don't have a sensor that measures bioeffluence, right? So in an ideal world, you'd like to have measure the bioeffluence, and then you could have some kind of activated carbon device that absorbs it, and you wouldn't have to ventilate, right? But we don't have sensors. Similarly, for infection risk transmission, there's no economically viable way to detect pathogens in the air. There's actually a lot of research going on. There's an ARPA grant that's going on right now to develop that technology. But today we don't have the ability to detect those things. So what we have to do is assume reasonable concentration or generation rates, and then prescribe mitigation methods that on the average will get you to acceptable concentrations. That's kind of the best we can do.
So are you referring to particle size and filtration or particle size and ventilation? Okay. So I don't know how size resolved that process would be. I mean, aside in absence of like super large particles that may not get entrained into the outdoor air intake, but I think for most particles below 10, 20 microns, they should be entrained into the outdoor air intake. Is that what you're referring to? Okay. I don't know who has investigated that particular process. Certainly, I mean, filtration is obviously very heavily size dependent. Deposition to ventilation duct surfaces does occur for both very small particles and very large particles. And that's something to consider if you are doing some modeling of particle transport throughout the entire, like a very large scale commercial HVAC system. There will be deposition to the ventilation duct surfaces that would have to be accounted for, which leads to things like duct cleaning that have to be done. I think in a general sense, we have a lot of data on like size resolve indoor-outdoor ratios for different types of situations that are helpful to look into. But I think with respect to particle transport throughout a HVAC system, the most important thing would be removal via filtration in terms of size-dependent dynamics versus kind of bulk aerosol motion, I would say. Maybe there's some size dependency that affects the extraction efficiency of a kitchen hood, perhaps, but I'm not so familiar with that. Like adhesion forces? Yes. Yeah, I think that's something that could be quite variable among different types of particles. Yeah, with respect to attachment to surfaces and detachment from surfaces, for example. Yes, for different types of biological particles and organic particles. I think one thing you mentioned about like different types of particles in general to control for, yes, we don't have really good low-cost sensors for that, but I think that maybe in the future we will have some miniaturized mass spectrometers and things like that that could give us some useful information that could be coupled with ventilation control strategies. I think it's like, where are the particles coming from? You know, cooking emits its own signature combustion, people, dust that may be resuspended. So you could have some information about the chemical composition of particles from different indoor and outdoor sources that could be perhaps coupled with a model and building automation system. If you want to, you know, focus on different particle types, you know, look to where they are coming from, perhaps.
So maybe the first one is a comment to what you said and the previous question that Shruti asked. So, you know, in the advanced materials community now, I in fact gave a talk yesterday on using a life cycle analysis and the concepts of circular economy. These are coming in a big way. So my suggestion, or just a comment, is that the consumer industry, and we have experts here actually on our faculty, to work with individuals like you and then do an appropriate life cycle analysis, which will also put a metrics label out, right? So you draw the boundary now around the consumer in your case and really quantify it. And there are tools available to do that. Giving up, of course, is an idealistic approach, which is always good. And but maybe something like this would be better, and especially from a public health perspective, all won't be as idealistic as you are. Now, my question, which I was asking you, I want to challenge the Purdue team, right? You gave beautiful talks, all of you, by the way, so this was fascinating to hear. You talked about nanoclusters. I presume I got it now that the fuel, the burner is a primary source of these nanoclusters, and please correct me if I'm wrong. And I know you were cooking also simultaneously, which was more a scavenger. So the nanoclusters have a characteristic lifetime, right? Today I'm on a life cycle analysis now of aerosols. So you could calculate that. If nothing else was there, they could also self-coagulate. You have high concentrations and move to larger sizes. So that is one comment. And what do we do about it, or what is the cooking contribution? So is cooking actually help scavenging? From what I could pick up, it is. So that is an important factor, right? And the deposition in the head region, I think that's a very serious factor because that's also a pathway oftentimes to the brain, right? So my question though, this is again, just clarifying, so thanks again. But the question is, there's a big push to get rid of coal combustion. Now I'm talking of big power plants and move to gas-fired burners. We have done that in the US. People don't see these small particles. So a gas-fired power plant is emitting large volumes, concentrations of nanoclusters. Lifetime may be short. The ESP, they still use particle control devices. Those are very ineffective at those small sizes. In fact, we've done very detailed work. So this becomes a challenge. Then what is it doing to the atmospheric aerosol? So I thought that should also be brought out, maybe as a comment. If you have thoughts, I would love to hear from you. But the question now, my Purdue University challenge, you'll work together. What is the chemical composition of these nanoclusters? And you have just sitting next to you, she had fabulous tools. She talked about hairsprays, but I'm sure you all might have worked together. It would be very interesting to understand the pathways. And I know Yang did some fabulous work with burners, but more in material synthesis. So it also gives you an understanding. Again, I put on my engineering hat always. You could design burners to suppress nanocluster formation, maybe, right? So maybe if you have thoughts, and please work together and map out the chemical composition of his nanoclusters.
So thank you, Pratim, for your insightful feedback on our nanocluster aerosol study. To think a few things. So I think, you know, in general, in indoor air quality research, we're not thinking so much about these very small particles, perhaps just broadly within air quality research, indoors or outdoors. And as you mentioned, with natural gas power plants as a potential source, I think they're certainly very important. And I think they should just be measured more routinely, whether it's directly from the emission source, so like in a kitchen environment, or from the kitchen exhaust vent itself to the outdoors, or from power plant exhaust, vehicle exhaust. Number of studies from Tampere University on different types of engines and their production of nanocluster aerosol. As you mentioned, more controlled combustion studies and so forth. And it's just like these ambient measurements, I think, would be very helpful for us. And certainly, I remember when I was at University of Helsinki, this was a big focus in their group there of Marco Kumala and others, measuring the nanocluster aerosol. And I remember I was there over a decade ago, and I saw this Air Modus instrument, and it was like a big deal measuring these small particles. And I think they were very interested in just the fundamental processes of nucleation and growth from the outdoor perspective. And, you know, I thought, well, what about indoors? And certainly they're indoors and they're being formed indoors, whether that's combustion or secondary processes, they're there. And one thing we looked at in a paper that will be published in ES&T Letters was the survival probability of the nanocluster aerosol. And we did calculate that for production of the nanocluster aerosol from these terpenose analysis reactions and compared it with outdoor survival probabilities. So I think a key factor was the extent to which the coagulation sink was present, whether that was a cooking process or when we had these secondary organic aerosol formation events. As we grew to larger sizes, the coagulation sink would grow and there would still be nucleation occurring. So there was kind of this fight between the vapors nucleating versus the vapors condensing on the pre-existing aerosol. And we characterized that, and we found in case of some of these fragrance products that even though there could be a very large coagulation sink, much larger than outdoors, there with some of these very high terpene concentrations and even low ozone concentrations, you're still able to drive nucleation at very high coagulation sinks, much higher than outdoors. And I know this has been looked into outdoors in terms of suppression of new particle formation at high Fuchs surface area concentrations, high coagulation sinks. And we see that indoors, because of the uniqueness of things like the gas stove as a very potent source of nanocluster aerosol, or these terpenose analysis events, that actually you can sustain the nanocluster aerosol concentrations at elevated number concentrations, even when the coagulation sink is much larger than you would have even in cities like Delhi and Beijing and Shanghai, just because there's just so much of this stuff being produced. The gas stove is a little bit more obvious as a source of particles, but one thing I didn't present on was a secondary production, and Nusrat discussed this, but indoors at these fragrance products, the terpene content is so high that it's like a forest on steroids. I mean, the concentrations of terpenes in the forest are maybe few part per billion or something like that. We can get hundreds of part per billions of these monoterpenes like limonene and alpha-pinene, and also monoterpenoids like linalool. And even at low ozone, like 10 parts per billion, you can drive the production of these low volatility vapors that can nucleate at very high coagulation sinks. So that does then increase the exposure to the nanocluster aerosol over an extended period of time. Eventually they'll be removed or they'll grow. But I think it's going to be kind of more looking at the short-term source events. If you're cooking or there's some combustion source present, or you're using these fragrance products and they react with ozone, you have this burst of nanocluster aerosol for some period of time until they're lost due to the various removal mechanisms. I think that in terms of their persistent outdoors as well, there was a very nice study from Tampere University on the traffic as a source of nanocluster aerosol, and they see these elevated number of concentrations along the road. So they're produced through primary and secondary mechanisms, and they're lingering around and remain elevated, well over 1 million particles per cubic centimeter. So I think that they're there. We've also seen that they react with skin oil, so there can be formed around your body. And I think that we really don't know too much about their chemical makeup. I think a nanocluster aerosol produced from an ozone reaction with skin oil is going to be much different than that produced from an ozone reaction with limonene versus ozone with linalool, which is added to many fragrance products, versus something coming from a propane stove, which may be different from a stove using other fuels. So the chemical makeup, I think, is something that they have studied for sure outdoors, looking at the highly oxygenated molecules and using various chemical ionization mass spectrometers, which we really haven't done too much indoors of that type of technology to characterize their chemical characteristics and how that may change over time as the particles linger around for some period of time, as they grow, as they coagulate with larger particles. I think certainly the toxicity would be not only a function of size, but the chemical makeup. And a nanocluster aerosol coming from a gas stove is not going to be the same as produced from a new particle formation event, and they may be associated with different toxicological health outcomes. And as you mentioned, like the translocation to the brain with the head airways deposition, I think is important to certainly consider. I think maybe even beyond that, in terms of the persistence of these particles, calculating survival probabilities and things like that, is trying to just to emphasize that ultrafine particles are not accounted for with PM2.5 mass-based metrics, which is what we have in the United States. I think we need to think about just measuring ultrafine particles in general, even if they maybe only go down to 10 nanometers or so in size, using lower cost technologies like diffusion chargers, things like that, low cost electrometers. Because if we have long-term data outdoors and indoors, I think that can then help us establish the links with adverse health outcomes. And there are studies that have done that, but it's not routinely done in the United States. And, I think that we're missing a big part of the air pollution pie by not measuring ultrafine particles routinely. We have PM2.5 mass, and other things, some trace gases, but we don't measure ultrafine particles routinely really anywhere in the United States. And just measuring concentrations would be a step forward. Measuring size distributions would be even better. Looking at the dynamics indoors and outdoors would be helpful. And of course, the chemical composition of ultrafine particles themselves, I think, is not well characterized in indoor environments because much of the work is more on the bigger particles, which aerosol mass spectrometers can detect, maybe down to 70 nanometers, something like that, 60 nanometers. But as you get to the smaller sizes, we just don't have so much data. And the chemical complexity of the indoor atmosphere is such that I think that the composition is going to be different from one home to the next, depending on what is going on with cooking and cleaning and so forth, ventilation conditions, use of all these aromatherapy products. So I think that there's just a lot of work to be done on ultrafine particles indoors and outdoors. And if we had some number-based exposure guidelines, I think that could help drive some of this research. And I think certainly be helpful if the EPA would start monitoring these particles routinely. And then I think that would drive more fundamental research into their dynamics and their survival probabilities and things like that, because, you know, could go hand in hand with the regulatory work on these small particles. But they're definitely prevalent and can be at much higher concentrations indoors than outdoors. And if you're just measuring particle mass or looking at particles of an optical-based particle counter, you'll never see these small particles. Doesn't mean that they're not there and not driving some of the adverse health effects that we see with things like gas stoves. Okay, yeah, I can go on a long rant about ultrafine particles. Sorry.
Pratim, thank you so much for really coming to our presentation and for engaging with it. I'm so excited that you came because I thought you are so busy. So thank you so much for coming. I did want to say that in addition to the coal-fired plants that you mentioned, I feel as if NCA should be classified as its own class of pollutant. And if you can do that, you can measure it. If you can measure something, you can regulate it. So it is very important that we as a scientific community start to talk about classification so that we could bring that to the government so that it can actually be measured. So if we are not measuring it, we simply just don't know anything about it. So I think starting from measurement and then classification, communication of this information, and hopefully regulation. It's always really welcomed in terms of protecting human health and our prosperity. Yeah, and thank you for exciting us with the ideas of chemical compositions. We have discussed it multiple times. I think we both need to sit down and write a proposal together. So thank you for that.
So my question is specifically to Dr. Shukla. Thank you, Dr. Shukla, for a very informative presentation. I'm wondering to know, is there any precise dose of any microorganism to consider it as being in an airborne transmission? Like sometimes we struggle to collect the viable organism when the concentration is low. And sometimes we have seen like the patient is positive, but we could not collect any single virus. But in the other events, we got some. So is there any precise dose? Also, would you like to recommend would you like to suggest or recommend something to the current bioaerosol samplings to enhance the viable microorganism recovery post-sampling? Thank you.
So I guess the short answer is it really depends on the pathogen, how much inoculum you need to kickstart an infection. And most of those, if for what data is available, is usually from animal studies, which doesn't always correlate to humans. There was one human challenge trial for COVID that was done in the UK, and I can send you the papers. They've had a few now from that study, which in the US would just be considered unethical, but they actually were able to do it in healthy volunteers there. And so there is a specific inoculum that they exposed the participants to. I can send you that. But it's really hard to say. I mean, I think we need to define that. I mean, we struggle with that with standard infection control when we were doing an outbreak response. Most of the sampling we're doing is standard bacterial cultures from surfaces. And even in that setting, sometimes we'll have patients who are very known to have the disease, whatever it is, and we're not able to isolate it from cultures. So we've tried a lot of different culture media to try and get a better yield. But I think there's depending on the pathogen, there's just, I think, a trial and error type of time frame to try and figure out exactly what inoculum. But as far as how much you actually need to kickstart the infection in the person, there's a lot of variables, including their own preformed antibodies, prior infection, immune status, et cetera. It's a good question, though. I mean, we're great if we could answer that.
Okay, it's 4:30, so that's all the time we have for this session. Let's thank the panelists again for their wonderful presentation discussion. And also, that's the end of our workshop. I would like to thank everyone for coming over here and participate in the discussion. And at the same time, I also want to acknowledge two people, Dr. Yang Wang and Dr. Jiayu Li. They are the hands behind everything to organize this wonderful workshop. So let's thank them. And also there is a group of people working in different places, setting up the food, setting up the poster boards, and doing all these things. These are our students at the University of Miami, the Aerosol Association, AAA, our student chapter. So can students stand up? We can thank you. Thank you very much. That's all we have for this workshop. I hope you all enjoy the 3 days of different programs, and I hope we can see you next year. Thank you very much.